Hello, is somebody here?
Yes,
room?
I'm technical assistant. Now I will let the
Sediment Run is our assistant. Hello, is somebody here? I see that we are in YouTube. We are streaming already
yes,
now.
I'm technical assistant. Now I will let the
Do you see other participants?
yes, I will let them in now.
Perfect. Trygve,
Hello.
nice to see you. Are you in Oslo? I suggest that you will unmute your microphone and say something.
Hello?
Just
Hello?
hello.
Good day.
Can you hear me?
Hello.
Yes, I hear. Vasiola, do you pronounce your name correctly?
It's Vasiola, yes.
Vasiola. It sounds very romantic.
Thank you.
And Renat.
Hello.
Vasiola, Renat. Renat from St. John's.
Yes, it's early morning in St. John's. We've just received a message from Trygve that he cannot hear anything.
And Trygve, we are not able to hear you also. Probably you can check your microphone or something like that.
You don't hear me now?
Now we hear you now. Perfect. And I suggest
Okay,
might
but
be
I don't hear you.
presenter can just try to share screen. Let's start with
Okay, let me
Vasiola.
stop sharing my screen. Now be able to try.
Yes, Vasiola, please make your trouble.
Okay, now I can hear you.
Oh, sorry, I have forgotten to let the participants share their screens.
Yes.
So now you can try.
Okay. Yes.
Yeah. Oh, I see your screen. We see your screen. You should do something with presenter mode, because now we see your both screen.
Okay.
We see also next slide view.
Okay. I will reshare if it's okay.
It's a presenter view and view of, yeah. Now it's perfect. Just run the next slide to see how it's going. Perfect. Nice picture. Okay. Now I suggest that you will stop sharing and Renat can try.
Okay, just gonna try it soon. Just a second. Can you see this?
Yes, we see your not presenter mode, and let's go to presenter mode.
Is this better?
Yes, it's exactly what we want to see.
Okay.
Running smoothly. Do
Now
you
I
have
need
some
to stop
fancy
sharing.
video?
No, I don't like. I figured if I start sharing fancy videos, it's gonna eat most of my presentation. How do I stop sharing? Here. Okay.
Stop sharing. Now it's Trygve, your turn.
Yes.
Is it Roman with us already?
It seems that he tried to connect, but something happened. Couldn't.
Trygve.
It's fine. I have some videos
Fine.
actually, but let's see if it works.
Let's try a video.
Yeah, it works, right?
A little bit slow, but I think it will work.
Okay.
Better than nothing. I see some strange. Oh, perfect picture.
Seems like it's working. Yeah.
Yeah, it works. Even video.
Okay. Yeah.
But do we have our fourth presenter? No, it's room assistant with us, but we don't see Roman Guzenko. It means that
He
will
tried
not
to
have.
connect, but thinks that there is really something with his internet connection, so maybe do it later. I'm
But
I'm
you are in
checking.
contact with him.
Anyway, I'm checking if he appears. So if he appear, I will let him in.
Perfect. Perfect. We still have 4 minutes before we will start our presentation. Dear presenter, I just would like to remind you that we will need to keep very strict schedule because we have only 20 minutes for each, as all of you for presenters, so it's only 15 minutes presentation, 5 minutes for question, and also you should keep in mind that YouTube broadcasting a little bit with delay, so the question might be come later. So they will try, if they will write the question, we will have it a little bit later, but I will try to follow it on YouTube, and we will see.
Will you notify us when there's like 2 minutes left, or?
Yes, I can, for example, do some kind of reaction. For example, can you see my hand or something?
Yeah, but I don't
we
know if
can
I could. Can we
have a
see
green
that in the
hand.
presenter?
Let's
Can we
have a
see that
green-
in the presenters mode? Or
I think no, you are not able. I reminded yesterday when I presented, I saw only me and only. No, I saw 2 screens. I don't remember what. But I can say you that it's 2 minutes left.
So
Okay.
now you can try.
good.
On YouTube now only visible how Fasciola starting. So it's 2 minutes might be, even 3 minutes delay.
Actually, it seems that it's a little bit less. Maybe you have the moment of translation beaten fast.
I don't know. But now on YouTube broadcasting is a trial of Fasciola. But never mind. We
Okay, we
just
will check.
need to keep in mind that we can have a question later. Now, what I see on YouTube now is Renat trying. This is how.
So now I have to start the recording on my computer in case of something with YouTube translation. So if something happens, we will be able to put this presentation later.
Recording and translation, it's separate things.
Yes, we we just record in case something happens with YouTube translation.
Okay, let's start recording and let's. Yeah, we see this information. Okay, continue. So, dear colleague, let's start our session. Session number, I don't see, 16, formation and evaluation of natural and artificial ice features. We will have 1 hour, 20 minutes for our presentation. I would like to present myself. My name is Natalie Marchenko. I work in the University Center of Svalbard, Norway, Longyearbyen. Svalbard, it's an island on the halfway of to North Pole. It's quite remote. We have all Arctic all around. It's actually my 8th presentation. 8th participation in POAC. I started POAC in 2007. I see Renat also trying to remember his first presentation. I remember you quite many times. So, and that's why I see some kind of responsibility for POAC running well. So I am geographer initially, and all your presentation will be very interesting for me. And I see we have a quite nice range of presentation. We will start with laboratorium, lab experiment, and via modeling, we will come to field and trial. So I'm looking forward to our session, and I will try to keep you in time. And with this, I give the virtual floor to Vasiola, and I hope you will present yourself and your co-author rightly, because maybe I can have mistake in pronunciation. Please, Vasiola, the floor is yours. Present yourself and your topic.
Sorry. Hello to all. My name is Vasiola Jaka. I am a PhD student at Luleå University of Technology. I'm going to talk today about brush ice formation on laboratory scale. My co-authors are Robert Bridges, Professor Kai Riska, and also Professor Andres Virsen. The presentation consists of the introduction to the topic, the aim of the research, followed by the test program measurements, called here test number 1 and test number 2. As well, we are going to discuss the brush ice channel formation in both test and development, and we will give some results on level ice and, of course, equivalent brush ice estimations resulted from these 2 tests. We will conclude with 2 conclusions, main conclusions drawn out of these laboratory tests, starting by the introduction. So the brush ice actually is formed mainly in the ice-infested waters that are frequently navigated. The main parameters that affect the brush ice accumulation are the cumulative freezing degree days, cumulative temperatures, and as well another main parameter is the breaking frequency. In addition, it can be the ship design as well as other meteorological parameters like radiation and snowfall, as we are going to see later on in the results of this research. The main challenge in port areas are actually maneuvering of the ship in heavy brush ice conditions, as well as berthing of the ship in of a vessel in heavy brush ice conditions. On the other hand, heavy brush ice in fairways can also cause, for example, delay of navigation, hindering of navigation, and brush ice in general can cause an overall unsafe operations. The main aim of this work is to characterize parameters that influence the brush ice formation in a small-scale tank exposed to outside weather conditions in mid-December and mid-January. The experiment were run in the University of Technology in Luleå, Sweden. Another aim was to evaluate the efficiency of replicating the brush ice development on a small-scale tank. As such, a steel tank with inside dimensions of 65 centimeters width, depth of 120 centimeters, and a height of 180 centimeters, a length of 180 180 centimeters, was insulated with a styrofoam at the bottom and side walls, and was filled until 1 meter with tap water that had an approximate water temperature 8 degrees Celsius when it was initially filled. A window was open in the height of the tank, actually 1 meter to 90 centimeters, between 90 centimeters and 1 meter in height, just to observe the underwater brush ice formation. 4 thermocouples were mounted to continuously record the temperatures of air and as well the surface temperature and the temperature in depth of 3.5 centimeters and 10 centimeters. The first test lasted 8 days. The 4.5 days, their temperature varied from -2 degrees Celsius to 2 degrees Celsius, and mainly the water was losing heat. And the last 3.5 days were actually the days that the brush ice formation was carried out, and their temperature varied from -5.5 up to 0 degrees Celsius, and had an cumulative temperature of 10 freezing degrees days within these 3.5 days. The second test, conducted in January 2021, lasted in total 3.5 days. Their temperatures varied from -25 up to -1 degree Celsius and counted a total of 35 freezing degree days. During the first test, the brush ice formation occurred by manually breaking the initially levelized sheet of 0.5 centimeters with a triangular shaped metal plate which had a width of 14 centimeters. This initial breaking procedure, or this initial passage, was always followed by 3 other passages of vertical metal plate that had a width of 7 centimeters. The first brush ice channels was broken in total 13 times. The second brush ice channel, though, was broken initially with a hammer, and 3 other passages were following the first passage. The 3 other passages were conducted the same way with a vertical metal plate with the same width. The first breaking event in this second test occurred in a initialized thickness of 1.05 centimeters, and the channel was broken in total 17 times. Here we see a set of photographs from the first breaking event that identifies the brush ice development. The photographs actually from first to third shows the top view of the channel. After second, the first photograph shows the top view after second, before 10th, and after 12th breaking event. And the underwater view of the channel, it's showed for the brush ice after first, third, and 13th breaking event. After the initial breaking event, the brush ice flows, or the ice pieces that were formed, had a width almost equal to half of the width of the channel, and the initial breaking events during the initial breaking events, the ice pieces were mainly moved sideways to form this, as we see in this picture, in the 5th picture, the side ridges. Another effect that was quite noticeable during both tests was the effect of snow. In this case, the snow occurred between 9 and 10th, initially between 9 and 10th breaking events, and the snow contributed to a slush accumulation in the channel as well as in the adjacent ice structure. But this slush that accumulated actually after the breaking event had the tendency to mainly extend it it was extending vertically instead of moving sideways. So the ice concentration in the channel increased with the snow accumulation. During the second test, what we noticed is that the flows in this time were bigger than the first test, and they reached almost the dimension or the width of the channel. And because of the snow contribution, or the snow occurred earlier, also the ice concentration was much higher from the earliest breaking events. But also the freezing degree days, of course, contributed, because the ice thickness increase was much higher compared to the first test. The snow and ice thicknesses were measured along the cross section of the tank every 5 centimeters. And here we see an example of the channel thickness, total thickness development with breaking events and time. What we should tell actually is that the thickness is the thickness of the consolidated layer only. We were not able to, or we didn't measure the slush accumulation under all the pieces that were loose. So therefore, what we can see from the picture is that the level ice, or what we called later on the thickness of the ice in the edge of the tank, was increasing with time, as well as the thickness of the ice in the ridge, in both ridges. However, I can say that we did a measurement of the slush in the end of the test, during this test, and the slush accumulation, or the thickness, was almost 10 centimeters in the end of the test. That wasn't able to actually be measured, or we didn't measure it. Another parameter, the width, the channel's width, in this case, was measured along the channel's, the tank's length, by recording pictures and by estimating the width after each breaking event. What we noticed is that the width of the channel was decreasing actually with time and breaking events, and what we think is that this was a result of the manual breaking procedure itself, because the thicker the ice was getting, the harder it was for us to break the ice. And we reached a point in the second testing, in the second channel, that we couldn't break the tool, the 14 centimeters tool, that couldn't actually break anymore the ice or pass anymore the channel, as we can see here. We continue with the thickness, or level ice estimation. The diamonds, or the points here, show the average measured values of the level ice, or the thickness of the ice in the edge of the tank, in both edges of the tank. And we try to estimate, or we used Stefan's analytical formula and Ashton's analytical formula to estimate the growth of ice. And what we see is that the theoretical alpha compared to the empirical alpha that gave the best fit for the Stefan's equation have a high difference, as well as the theoretical alpha, or Stefan's equation with the theoretical alpha, overestimates the actual thickness of the ice. And the best fit for Ashton's equation was a convective coefficient equal to 22. Here we see the brush ice estimations, or actually the equivalent brush ice estimation, and also the thickness of the level ice, or tank's edge thickness, just for comparison, where it stands with the equivalent brush ice thickness. For the equivalent brush size thickness in this case was simply estimated or simply calculated from the measured values based on two assumptions that previously have been introduced previously by Sandqvist. The first assumption was that all the ice was remaining in the channel, and the second assumption was that the channel had a width equal to the equipment's width that formed the channel. Under the same assumption, Sandqvist actually proposed an empirical model that counted only the freezing or the cumulative freezing degree days and as well the breaking frequency. However, an overestimation of the values it's noticed during the test, and we suspect, of course, that it can be because of the thickness of the slush or ice that wasn't measured, and second because the model itself doesn't count, for example, porosity, as well as the snow contribution can be a parameter that have affect such overestimation. To conclude, the experimental setup was a preliminary test aiming to provide insights into the overall method reliability. The tests highlighted the effect that the braking procedure, the manual braking procedure, as well as the initialized thickness have in the piece size distribution and the width of the channel. And also the test highlighted the effect that the snow had in the brush ice accumulation, and as well in level ice accumulation, even though we didn't actually study it in this case. We would like to acknowledge Total Energies and Colarctic Project for supporting this work. And as future work, we are planning to study the snow effect on the brush ice development, the initial level ice thickness effect, the breaking frequency and breaking procedure effect on the further ice accumulation, and the long-term sidewall effect, which we didn't actually study in this case because the tests were run for a short time. I want to thank you and very much for your attention, and I'm waiting for your questions.
Thank you very much, Fasiola. Perfect presentation. You kept in time perfectly. I don't see right now any question. Oh, I saw in the YouTube. Anna Baker asking you, she wrote, thank you, Fasiola. Are you able to comment on how show may influence brush ice, snow may influence brush ice in a large scale, full scale?
Yes, this winter we have been studying this phenomena actually in a full-scale brush ice channel, and we have noticed that the brush ice, of course, the snow have two effects. One of them is insulating between two passages if actually the channel is not frequently navigated, and this winter we had a huge amount of snowfall, reached 50 centimeters, and because of this amount of snowfall also contributed in the thickness or in the slush and snow ice formation, both in level ice and just on level ice, and also in the channel. So we believe that in winter that the snowfall is high, the contribution also of snow ice in the channel is also higher. So we believe that it adds in the thickness of the channel.
Thank you very much. Might be somebody from audience have a question. Renat, Trygve, Roman, you have privilege to ask directly.
Hello.
Hey.
Hello, everyone.
Yes, who is asking?
I am Roman.
Roman, please make your question if you have.
No, I haven't question. Good presentation. Thank you for presentation.
Thank you very much, Roman.
Yes, if somebody from YouTube or from audience will have a question in future, just write your question in the chat place. And with this, we should come to the next step of our session. And we are very welcome Renat with his presentation.
Yes, hello everyone. Just let me share my screen first.
Perfect. We see your
Can
screen.
you confirm that you see it full screen now?
Yes, it's full screen now.
Okay, I guess I'm gonna be starting. My name is Renat Yulmetov. I work for Seacore in St. John's, Newfoundland. Seacore stays for Center for Cold Oceans Research and Engineering. It's a small nonprofit company. We're dealing with harsh environment projects, starting basically from seabed up to satellite imagery. Today, I'm going to talk about iceberg drift modeling using machine learning. This is already the second generation of the approach. The first generation was presented 2 years on POAC in Delft. Unfortunately, I was not able to attend. Freeman Ralph presented, but at the same time, I was preparing for an offshore expedition to collect more iceberg tracks that you will see in this presentation. So in short, you know, the iceberg drift modeling is very important, both for climate studies and for engineering. From engineering perspective, it's a critical part because you need to do trajectory forecasting to figure out if an iceberg approaching an offshore facility is going to contact it and cause any damage. And then it's important to know velocity of iceberg before the contact to assess the threat. And then this will help you to take decisions whether you should disconnect your facility, should you evacuate, or take any measures such as physical ice management. So that potentially saves a lot of downtime per season, and that converts into money. So for instance, some seasons are very, very busy. 2009 season, we had more than 1,500 icebergs crossing 48 degrees north. Was very busy season for offshore, and of course, lots of towing, lots of forecasting. Since, you know, it's very important, but it carries lots of uncertainties because icebergs drift under action of hydrodynamic forces caused by ocean water and wind. And usually when you forecast an iceberg, you issue a forecast based on the weather forecast, which is the last thing you want to do, especially in Newfoundland where currents are very complex. And to solve this problem, people approach differently. There are dynamical and statistical approaches as extremes. In dynamical approach, you have Newton's equation of motion that you solve for an iceberg, and you integrate it in time to figure out the trajectory. In the equation of motion, you use drag forces and for wind, and hydrodynamic forces for water that consists of drag force and Fruit-Krylov force. And in statistical approaches, people try to build empirical relations between iceberg velocities and met-ocean data that corresponds iceberg velocities at that time. And there are all sorts of hybrids that try to take the best of the both of approaches to tackle uncertainties. I tried to use machine learning because I felt there's more and more data that we're able to collect, and that was a perfect case to apply. And for those of you who are not familiar, which I doubt, about machine learning, it's a large set. It's a very general term describing large set of technologies and algorithms that help you to use data that you have in one way or another. There are classification problems, there are regression problems. In this case, in case of iceberg forecasting, I'm going to be using regression algorithms. This image that you see is just a a variety of algorithms as a starting point when you pick an algorithm on one of the popular libraries. So there are tons of algorithms, and I used one of them, and I'm going to show you how it worked. So the large branch of machine learning called supervised learning is an approach when you're trying to build a model and you based on observations, and then you use the model to forecast, to predict something that you don't know already. So in relation to icebergs, let's say we want to predict future location or future velocity of an iceberg, and we know meta-ocean conditions. And to do that, we collect many iceberg trajectories and study at what conditions they drift. So in the first stage of the process called training, we build a model. We start from some initial state of it, and we feed some input data into it and ask it, look, this iceberg is drifting with this certain velocity, and wind conditions are going to be this, and ocean currents are going to be this. Where it's going to be? What velocity we should expect on the next time step? And then because we know trajectories and velocities of icebergs, we get some result and we say, oh, look, there is some error. Your model prediction is not as accurate as reality. So we adjust the model based on the error we receive. And we do it iteratively many times until model converges to some level of error. And we hope that error is reduced. And then when we look at now an iceberg that we have not tracked, or an unknown iceberg, we use the model in prediction mode and we predict the drift velocity, which is unknown. To be more accurate, or to provide more details, the new approach that we're using, by the way, the old approach that we used was just exactly as this. We had a black box, we fed iceberg drift velocity, wind and current velocities into the black box, and we got drift velocity on the next time step, and which we integrated and found iceberg trajectory. In new approach, we hybridized it a little bit. We took kinematic equation, which you see here on top. This is iceberg acceleration, du divided by dt. Then we have a Coriolis term. And on the right side, A is acceleration that is caused by a combination of wind drag forces and hydrodynamic forces. If you discretize it, you can discretize this equation in a variety of ways, but just for example, if you use implicit scheme, you're going to get this system of equations. And then in training process, you train the model, you know velocities of your iceberg because you have trajectories, and that means you can calculate accelerations A, and you train the model to predict those accelerations based on meta-ocean data. And when you use the model for actual predictions, you predict accelerations and solve this system for ui+1, which is velocity of iceberg in the next time step. And then you do it iteratively 24 times, 24 hourly time steps, integrate velocity that will give you 24-hour trajectory forecast. For the algorithm, we use gradient boosting in this generation. In the first generation, we used neural networks, but there are some issues caused with input normalization, and we were just trying more different algorithms and figured out that gradient boosting works really well. We used CatBoost implementation, which is open source implementation that is able to run, which is scalable and can run on GPUs, but I won't concentrate too much on that. So where do we get data? In 2019, we went offshore. We had 4 voyages. We had a big campaign with primary purpose to GPS tag icebergs. We tagged them using drones. That was UAV deliveries. We had a pilot on board and several drones with special delivery mechanisms where when you fly over an iceberg and then you release the tracker on a rope, and when you land the tracker on the rope, you cut the rope basically. We put more than 100, about 110 GPS trackers on icebergs, but many icebergs were in the later stage of development, I would say, and they actively rolled, and we lost many trackers within just a couple of hours from deployment. But we had some longer tracks which lasted for a couple of weeks. And some icebergs were grounded, especially those green icebergs you see on the map to the north of Labrador. Those were large icebergs. And I removed that data too, because grounded icebergs would bias the training process. I used HiCom for currents and CFS model for winds. Those two are large gridded models, large scale gridded models. I would prefer local measured currents, but of course we didn't have a luxury to have an ADCP on board. We also did 3D profiling of every iceberg that we encountered, not every iceberg that we encountered, but majority of the tracked icebergs. So we had accurate dimensions. I couldn't stand, and I just plucked an eye candy photograph of an icebergs we encountered. There were many, many beautiful icebergs. It was really nice weather sometimes. And just to demonstrate that the 2019 season was very busy and we had lots of icebergs. To the right here, you can see a photograph of the radar with 8 icebergs within 12 nautical miles. All those red dots on the radar are icebergs. So we were surrounded by icebergs and we had lots of work to do. Just a couple of examples of how the model works. Just 2 random examples of trajectories, and one is more or less okay, and another one is not really. The dots on the trajectories are separated by 1 hour, so it's 24-hour forecasts. You can just qualitatively see that the model drives icebergs in more or less right direction. It doesn't push them opposite way, but still there is lots of things that we can improve. How do we say which forecast is good and which is bad? We can measure the distance between the predicted iceberg location and actual iceberg location. That will be an error. And then if we look at this error in time, we're going to see error curve. But we should be careful with it, because in this slide you see 2 examples of forecasts. In the first case, iceberg drifts about more than 35 kilometers, and in the second example, iceberg drifts less than 10 kilometers in length. In both cases, the error level is approximately the same, but you can qualitatively say that the first forecast is much better than the second. So it needs to be, the length of the track should be taken into account. But if you use that, if you try to optimize for that, then you start losing your average error. So we should, in future development, we should be careful about that. And just saying it because I find it's very interesting. So in the results, once we did lots of forecasts for those icebergs, every 24-hour chunk, we would issue a forecast. Then we would look at the average error and compare with other forecasts. I did k-false cross-validation, because if you use your whole training data set for testing, it will be biased. We've got about 11.6 kilometers error for this data set. What we can see, it is definitely performing definitely better than the methods that are currently used offshore. But some newer models, as for example Ian Turnbull's or Leif Anderson's, it is comparable result. If you can also see at the error distribution the plot in the bottom right corner shows you how 24-hour error is distributed. As I said, average error is about 11.6 kilometers, but sometimes we received errors about 35 kilometers or more. But the most likely error is going to be less than 10 kilometers. The implementation of the model is a part of the operational tool that we developed for an offshore client. In the tool, you can pick the model. There are 4 different models you can pick, run it, and the software delivers your T-time and closest point of approach to your software facility, depending on your inputs. What's next? Basically, first of all, I would like to collect more data. Personally, one of the reviewers suggested to bring in fruit Krylov component, and I started to experiment with that. So far, I'm getting the same level of error, but I need to spend more time investigating it. We've collected size data on icebergs as well, so I will use that for training. Satellite imagery is coming. That would be interesting to try. And there is some more algorithmical improvements to be done. This is it. This slide is just some references about the data we have collected about the first generation of the model, and the photographs you see is what we did during 2019 campaign. This is the vessel we used and the profiles we obtained, and drawn with the tracker placed on an iceberg. Just for those interested. Thank you very much. I'm open for questions. And I can see there are some questions in the chat, but I am not able to read them, I guess.
Thank you very much, Renate. Perfect presentation, as always, exciting, and a lot of good information. I see that we are 18, 19, 20 in the YouTube channel, so we are even some like champion among our free section. But I'm not able to see any question right now. Dear colleague, please be more active. It would be nice if you will write some words in YouTube just to let us know that you're with us. We see
I
Anna
have a question
Barker.
if I may ask.
Yes,
Of
absolutely.
course,
Yeah.
Trygve, you are first priority.
Okay,
Please
thank you.
go ahead.
Thank you for a very nice presentation, Renat. It was very interesting, impressive work, and very cool photos. I was just wondering about the data you use, or the observations you use for the training of the model. I suppose that's the term. So you mentioned that you have used some wind and sea current hindcast data, I assume?
Yes.
And you use GPS tracks. What about waves? Do you have some wave information as well?
At that year, we did not collect any wave data. We have a couple of wave buoys placed close to Avalon Peninsula, St. John's, but that was quite a distance from the place where we had icebergs tracked. It would be interesting to use wave data, I know it, and we have written a proposal to the partner, but then COVID struck in 2019. Yes, I would like to use wave data.
Okay, yeah.
But it needs to be accurate. That's I would yeah, that would be very curious.
Yeah, because I assume that would influence the drifting.
Yes, we had different weather conditions. So I spent more than about a month offshore in 2019. So we had storms and we had nice weather. And it's interesting how when you have waves and you are among several icebergs of different sizes and shapes, some of them drift in one direction and others drift in a little bit different.
Yeah.
Okay, dear colleague, we should be very strict in time because we have a full program, and with that, thank you very much, Renat, for a very nice presentation, and we will go further to Trygve, please
Thank you.
share your screen. Renat, stop sharing your screen.
I'll have to leave now, but thanks a lot.
Yeah, thank you.
Bye.
Thank you for your presentation. Good luck with your research. We will be waiting for your future
Bye.
nice results. Bye-bye. Give our regards to people in St. John's.
Thanks.
Bye-bye.
Okay, so do you see my presentation?
Yes, it's in full presentation mode. Please present yourself and your co-author and your title of your presentation.
All right.
Go ahead.
Thank you, Natalie. Thank you for the introduction. And hi, everyone. I'm Trygve, a PhD student at the University of Oslo. And I'll present for you now a study on iceberg stability during towing in a wave field. And my co-authors are Alexei Mashenko, Sean Rabot, Olav Gundersen, and Atle Jensen. So first a bit on the motivation for study. So icebergs pose a threat to boats and offshore structures and have been dreaded for many hundred years by sailors. The most catastrophic event that ever occurred was, of course, Titanic, here illustrated by this iconic painting by Stover. These kind of large accidents wouldn't happen nowadays because of radar technology and remote sensing. But there are still 1 to 2 yearly incidents in modern times. And this is partly due to that small icebergs can still influence damage on constructions, and they are more difficult to observe remotely. And when we have oil platforms or drilling vessels that are fixed in space, and we have approaching icebergs, this needs to be deflected off to avoid collisions. And to do this, iceberg towing is a well-known technique. Unsuccessful towing events are often caused by iceberg overturning or tow line slippage. And as it's a large mass suddenly moving, it could cause harm to people and equipment, especially these overturning events. So therefore, we have investigated stability of the icebergs during towing. The experiments were carried out in Temple Fjord on Svalbard. The red rectangle on the map there indicates the fjord, and that's also the position of the satellite image below, where you see on the top right corner, there's the Tuna Glacier extending out in the fjord, and frequent calving events makes it an ideal site for this kind of experiments. And the novelty with our setup is the extensive instrumentation. So as previously, mostly only GPS trackers or accelerometers have been used to measure the iceberg motion. We installed inertial motion units with GPS trackers to monitor the iceberg and the boat position and velocity. And we had a load cell for the tow line tension, and we had surveillance of meta-ocean parameters. And we used a remotely operated vehicle to investigate the subsurface geometry. I'll shortly show you a video of this. And for the above surface geometry, we had the camera images that were put together to make 3D models. As you see in the top right corner here. Thank you to Natalie for this. And this allowed us to accurately find the surface area at the water level S, which then together with the natural period of oscillation in heave obtained from the IMUs placed on the iceberg, plugged into the momentum equation in the vertical direction, we estimated the iceberg mass. And the mass of the icebergs was around 100 to 400, 500 tons. So technically speaking, only bergy bits, but we will refer to them as icebergs. So here's a video where we see a dive with the ROV to look at the subsurface geometry, and it's quite complex with a lot of fissures and cracks, bulks. And we originally intended to make a 3D model of the subsurface geometry as well, but the glacier sediments made the water quite unclear, and the pictures are a bit blurry and not suitable for making such models. But at any rate, we got a good impression of the geometry and the depth of the keel. So we used a sinking tow line, and that was kept at a certain level below the surface with floaters, these yellow dots on the drawing to the right here. So that's the tow line force was applied closer to the iceberg center of rotation. And this reduced the risk of tow line slippage and iceberg overturning. And the submerged line also reduced the risk of damage in case of tow line failure. And you see the drawing shows where we placed the IMUs, and the load cell was kept afloat by this red buoy. We performed 3 experiments where the trajectories are shown here. In gray is the free drift of the iceberg, while the orange is towing trajectory during towing, and the blue one is the boat. And the dots show 10-minute intervals. So in experiment 1, we towed along a straight line. In number 2, we tried to alter the trajectory as fast as possible. And in number 3, we had some incoming waves, and we investigated the effect of the waves by towing at different angles with respect to the waves. Here you see a time series of the first experiment. There's a lot of information here, but we will only focus on the pink line, which is the iceberg roll, and the green line, which is the towing load. So in the beginning here to the left, we performed 3 short accelerations with the boat, seen on the 3 small peaks on the green curve. And they induced some small periodic oscillating roll motion, especially when the load drops. We have large response in iceberg roll that is slowly damped. And eventually, further around 1520, this motion becomes unstable, and we have a transition to a new stable static position, because we believe that we observe here that the iceberg have several stable static positions, and when we apply some external force, the iceberg wants to sort of revert back to the stable position, or we can have transitions between the stable positions. This position was not so stable after all, because when we performed some more towing around 1530, the iceberg rolled around 90 degrees, and we were barely able to retrieve the instrument. I would also quickly mention the gray line, which is the distance between the boat and the iceberg divided by 10. So the distance was around 50 meters. And during this high moment of high load, around 1430, we see that the line extends a few meters. And this is a property that we will later use in the analysis. Jumping now to the third experiment, we had wind coming in this day and also wind waves. So we towed first, the direction was against the waves in this red area here, and then perpendicular to the waves in this blue area. And we observed some oscillations in the system here from the towing, seen in the towing load time series in green. And these oscillations are much more prominent. The amplitude is higher when the towing was performed against the waves seen in red here, as opposed to perpendicular to the waves seen in blue. So probably due to the extra induced periodic wave drag in the axial direction. And this is also found in numerical models. We also investigated this in the frequency domain. So we've taken the Fourier transform to obtain the spectra. And we see this peaks in the spectra at the oscillating period around 4 to 6 seconds. And you see that the peak is much more prominent when the towing is performed against the waves. So these oscillations can be attributed to two different phenomena, either the iceberg natural motion or oscillations in heave or roll. And that was observed to be periods around 5 to 7 seconds. It could also be due to the tow line elastic properties. And this has been investigated theoretically by Marchenko and Eich. That is the oscillations in the system consisting of the iceberg, tow line, and boat. And they've evaluated the momentum equation at steady towing and derived this expression for the period of the oscillations, TS. That depends on this derivative df dx, which is the towing force, with derived differentiated with respect to the distance x between the boat and the iceberg. And this property was found from the measurements, as I explained earlier, with the distance and towing load. We use this one and also the rope manufacturer data to obtain periods around 6 to 8 seconds. So both these two causes are plausible explanations for the periods. Let's see, yeah, I have a video here showing that the iceberg eventually rolled a bit. So it became stable eventually in the third experiment and rolled around 90 degrees. So it doesn't look very dramatic here, but it could be in a much larger scale. So unfortunately, the instrument was attached on the top side that was turning to the bottom side, and we tried to search for it, but a dive with the ROV revealed that it was still, attached to the bottom. So this instrument and data was unfortunately lost, but that's the nature of field work, I suppose. Just like Renat mentioned in the previous talk with lost GPS trackers. So to summarize, we have performed 3 iceberg towing experiments and presented technique with the submerged line proved successful in the sense that the tow line slippage was avoided. Although the iceberg turned over in some situations. And extensive instrumentation allowed for a detailed study on the dynamics of the iceberg and of the boat rope iceberg system. And we saw that the icebergs have several stable static positions, and that external forcing can cause a transition between the stable positions, which may lead to overturning. And we observed oscillations with period around 6 seconds in the iceberg towline boat system. And they are attributed to either the rope elastic properties and or the iceberg heave or roll motion. And these oscillations were significantly greater when the towing was performed against compared to perpendicular to the wind waves. That is probably due to extra wave drag on the iceberg in the axial direction. So that was what I wanted to present, and I would like to thank you for the attention.
Okay, thank you very much, Trygve, for a very interesting, even exciting presentation with this instrument lost and a nice video. Dear audience, and I encourage you to ask the question. Aha. Anna Barker from Canada again ask question to presenter now. Thank you, Trygve. She wrote, given the results showing the effects of directionality, how do you think this could be applied in an operational setting? Are there limits? How they can be applied? Trygve, do you understand the question?
Yeah, there was one word there I didn't capture, but so I assume the question is about how the results in general are applicable to
operational settings. Yes.
Yeah.
How it will work in reality.
Exactly. Yes.
And
so
any limits?
Yeah. So at least we saw that these oscillations in the tow line tension, they increase a lot when towing is performed parallel with or especially against the direction of the waves, and this could induce some peak loads that may of course grow in amplitude if the iceberg are larger and the contact surface that absorbs the wave force are greater. And this is important to remember when performing the operations, because the peak loads may exceed the strength of the towing rope, for example. So I think it's important at least to be aware of the effect of the waves. That is one thing. The other thing is maybe that the setup with a submerged tow line could reduce the risk of tow line slippage, but also to the overturning of the iceberg, although this did happen in one case for us.
Okay, thank you very much, Trygve. I realize it's quite difficult to run a presentation and question at the same time in online mode, and I'm very thankful to Anna Barker that she's able to join us from Canada, even with time difference. But thank you very much, Trygve, and with this we should come to the next stage.
Thank you for the
to
question.
Our big team from, not so big, but 6 COFOR from Arctic Antarctic Research Institute, ARI. Roman, I hope you will present your COFORs. Just start to share the screen.
Can I start?
Just start to share your screen. We will see how it will work.
Yes. Do you see?
No,
First slide.
I don't see your screen. Press a button, share the screen.
Yeah.
Yes, you're on the way. Double click, yes. Please make this presentation mode.
Yes.
Yes.
Do you
Now
see
everything
first
is
slide?
perfectly. Just go ahead.
Okay, I start. Dear colleagues, my report is devoted to study of a relationship between the consolidated layer thickness and other morphometric characteristics of first year ice ridges. Ice ridge is line of wall of broken ice forced up by pressure. First year ice ridges are ice features typical for all freezing water area. The key morphometric characteristic for taking into account the possible impact of ridge on marine infrastructure is the consolidated layer inside the ice feature. Consolidated layer is a layer in which all ice fragments are frozen together. The purpose of the study is to identify the morphometric qualities of ice ridges with the greatest average consolidated layer thickness and to consider the factors that determine the development of a heavy consolidated layer. This study is based on the result of complex studies of 129 first-year ice ridges carried out in 6 different regions of the Kara and Laptev seas in the spring period of 2007-2017. Work on ice ridges in region 1-4 carried out on drifting ice. Ice ridges in region 5 were studied on fast ice, and as ice ridges in region 6 were studied both on drifting ice and fast ice. The technology of thermal drilling with a recording of drilling speed on electronic medium the main method for studying the morphometry and internal structure of ice features. This technology has two modifications: electric drilling and water drilling. In first case, the melting occurred due an electrically heated drill bit. In the second, with the help of heated seawater. Both modifications have the key principle in common: the depth and speed of the drill's immersion in ice with a step of several millimeters are automatically recorded to the logger. The layers of ice are found as a result of interpretation of drilling rate changes. Consolidated layer in the composition of hard ice. There are examples of internal structure in the boreholes in the cross-section of various ice ridges with determination of a consolidated layer. Table shows amount of initial data. A total of 5,121 boreholes were drilled at 394 profiles. On average, about 40 ridges, about 40 drills were carried out on each ice ridge. About 1/3 of ice ridges, 41, were investigated on fast ice. Here, arithmetic means of the mean or maximum values of the morphometric parameters of individual ridges for the corresponding samples. Samples of ice ridges on fast ice highlighted. According to most the average parameter, the largest ridges were investigated in North East Kara Sea, region 2, in 2015. The ice ridges of the Baidarata Bay region 6 in 2010 are distinguished by the greatest average consolidated layer, 2.7 meter. The ice ridges of Khatanga Bay region 5 are characterized by the smallest values of keel depth, total thickness, block thickness, but the largest thickness of the surrounding level ice and the second largest consolidated layer thickness. The main morphometric differences between fast ice and drift ice ridges as follows. Drift ice ridges have significantly longer crests in 1.4 times, and ice ridges on fast ice noticeably exceed the average consolidated layer thickness in 1.4 times, and surrounding level ice in 1.5 times. The distributions of consolidated layer thickness over points on drift ice ridges and over points of fast ice ridges are shown here. Both empirical distributions are best approximated by the gamma distribution. The average consolidated layer thickness over points on the drift ice ridges was 2 meter and 2.6 meter along the points of fast ridges. The highest repeatability of consolidated layer thickness on drift ridges ranged 1-2 meters, and on fast ice ridges 2-3 meters. Histograms of the distribution of average values of consolidated layer thickness over ridges, the entire set, and samples along drift and fast ridges can be seen here. In general, ridges on fast ice in comparison with drift ridges correspond to a heavier consolidated layer with a smaller total spread of thicknesses. The consolidated layer thickness of ice ridges depends on the temperature regime of the local region. We attempted to estimate the average age of the ridges in the region starting from the average values of the surrounding level ice thickness and the ice block thickness. The relationship between ice thickness and sum of freezing degree days was determined by the classical formula of Zubov. First, using this formula, the date of ice floe formation was determined from the average thickness of level ice and data of the air temperature from the closest polar station. Then, using the same formula, the average date for the formation of ice ridges was determined from the model value of ice block thickness. The difference between the date of the middle of the study period and the date of formation of ice ridges in region correspond to the average age of ice ridges. The average age of ice ridges on drift ice at the time of the study was 3.3 months. Age of ice ridges on fast ice at the time of the study was about 5.5 months old. Apparently, the greater age of the fast ice ridges, first of all, explains their greater average consolidated layer thickness. Traditionally, the formulas connecting the ice thickness, H, and the air temperature are based on Stefan's law, Formula 1. Here, K is the empirical coefficient which we obtained for each region as the ratio of the average consolidated layer thickness to the square root of freezing degree days. The K values are given in rightmost column of table of the previous slide. The average K value by the region was 0.047, formula 2. And here are the similar equation by other authors. According of the data of 129 ridges, it was not possible to reveal a noticeable correlation between the average consolidated layer thickness and other morphometric parameters of ice ridges. A moderate positive correlation in a range 0.35, 0.51 was recorded between the consolidated layer thickness and the external parameters. The relatively low values of the correlation coefficient are understandable. The consolidated layer thickness is primarily determined by the thermal conditions and the duration of their impact, the age of the ridge. And the external morphometric parameters are mainly associated with the dynamic processes and ice thickness at the moment of formation of ice ridge. However, the positive values of the correlation between consolidated layer and all the external parameters of ridges in different samples indicate a general trend. Here, the main morphometric characteristics by 6 region agent was carried out when at least 2 ice ridges fell within the gradation. If only cases are marked in the table with footnotes. Gradation of the concept
Roman, something happened with your translation. I'm not able to hear you. And it seems that you're some kind of frozen.
Seems that Roman lost the connection because now I can't see him between the participants. Maybe he will have the time again.
I guess let's just wait for a while. Might be he will reconnect his computer because he had some problem at the beginning, as I understood.
Yes, something with connection.
Let's try and give him a chance. Do you have a phone connection with him, Alexander?
Well, I don't see him trying to connect. Maybe something serious.
I will write him email. It's really pity
Oh, I
that.
see him.
Mhm.
I see him trying to vote. Why I'm trying to let him.
Alexander, now also I don't hear you well. Your voice some kind of vibrating.
He's trying to log in, and I'm trying to let him in.
Mhm. Dear colleague watching us on the YouTube channel, actually we have only 3 minutes left till the end of our presentation. If you have some question, you have a chance to write it right now. I see that 20 persons are watching us, so it's quite a pity that we lost connection. But anyway, you had a chance to see a huge volume of investigation produced by Arctic Antarctic Research Institute. 129 ridges, it's quite an impressive amount. And the last table, okay, Roman, you're with us now.
I continue.
Start sharing your screen. We lost you on your huge table with blue and orange color.
Okay.
And you have only 2 minutes left till the end. Yes, this.
Okay.
This. Just summarize and come to a conclusion, because we have only 2 minutes left.
Yes. As
Yeah.
you can see from the table, the largest consolidated layer thickness gradation for each region correspond to the largest values of the most morphometric parameters. We can see a general pattern. Ice ridges with the largest consolidated layer thickness, as a rule, are characterized by the largest sizes. Conclusions. The age and accordingly consolidated layer thickness of fast ice ridges are significantly greater than that of the ridges on drift ice at the same time in the same or nearby region. Dependence of the average consolidated layer thickness on the temperature condition of the region is shown, taking into account the estimate of the average age of the ice ridges, the average value of the empirical coefficient showing the ratio of the consolidated layer thickness to the square root of freezing degree days was 0.047. Within the region, ice ridges with the largest consolidated layer, as a rule, have the largest external sizes, revealing and clarifying the relationships between external morphometric parameters on the one hand and characteristic of the internal structure of ice ridges on the other hand, deserve to be subject of future research. Thank you for your attention.
Thank you very much, Roman, for your nice presentation. Unfortunately, we lost you for a while, and unfortunately, we are coming to the end of our time due to strict time schedule. We just need to finish our session. But the beauty of POAC presentation that all papers will be published, and everybody will have the email and can contact offers directly. So please do the best of and use this opportunity. So thank you very much, all presenters. Thank you very much, Alexander, for your technical support in this difficult condition. And with this, I end the session and wish all participants and audience all the best. See you on the next section.
Bye.
Bye-bye.
Thank you.
Thank you.
Thank you very much. Goodbye. See you later. Они сами вырубили. Фу, ну с другой стороны это...
Огонь получился.
Так, нормально. Это нормально. Дима, блин, пишут постоянно.
Так, Саш, ты меня слышишь, да?
Да.
Все, сейчас меняемся. Давай мне права.
Так, получилось?
Да, теперь выходи из комнаты и выходи из учетной записи. Как только уйдешь, напиши мне в WhatsApp.
Так, стоп, подожди секунду. А я должен прекращать трансляцию?
Нет, 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 трансляцию оставь. Выйди
Ага,
просто из комнаты и выйди из учетной записи Zoom.
хорошо.
И напиши в WhatsApp. Так, Саш, ты меня слышишь, да? Всё, сейчас меняемся. Давай.
Так, получилось?
Да, теперь выходи из комнаты и выходи из учетной записи. Как только
Так, стоп, подожди.
трансляцию оставь. Из комнаты и учетной записи Zoom. И напиши в WhatsApp.
У меня айфону сколько лет? Afternoon, David. Can you hear me, David? David, can you hear me?
Oh, Sergey, no, I can't hear you. I just saw your note.
And now,
Oh,
I'm your technical assistant for this section.
Yeah, okay, I've got your audio.
Okay. I will keep track of the question, ask it in the chat on YouTube, and send them to you in Zoom, like personal message.
Okay.
Okay. Yesterday I listened to your lecture. It was great. Thank you.
Oh, about yesterday, you mean?
Plenary action.
I'm sorry, I guess I misunderstood. That's all right. So do we have any authors logged in yet?
We have one speaker, Valeria Sheluzonov.
Are we expecting all three, or is there going to be a recorded one?
Repeat, please.
Are we expecting all three of the authors to log in?
Yeah, I think we can wait 5 minutes.
Yeah, okay. So I'm sorry, which one is logged in now?
Valeria Sheluzonov.
Sheluzonov. Oh, that's the last paper.
Last
the third
author.
paper. Yeah. Sheluzonov. Okay. So Sergey, do you handle the screen sharing then?
Now we have two authors, Porubayev and Shaluzyanov.
Porubayev, okay. So we just need Dira Oliver Daman.
Yeah. I think it's time for us to start. I invite authors. Okay.
Okay, so the last author's logged in.
Repeat, please.
Do we have all the authors logged in?
No, we have not Oliver Daman.
Okay, so we should start and then hope that he logs in.
Oh, yeah.
Yeah. Okay. So the streaming has started. Good. Well, good morning, everyone, or afternoon, I guess, for most of the time zones of participants. I'm Dave Cole, and I'm the convener for session 19, the remote sensing in ice conditions forecasting methods. And we have 3 papers to get through, 20 minutes each. And so I'd hope that our authors all allow at least a few minutes for questions. And we've been told we do need to keep to the schedule as best we can. So with that, it'll be a little awkward in that questions from YouTube viewers will get transferred to me. And questions from among the participants will be handled directly through the Zoom conversation that we have going on now. And I think, yeah, we're ready to start. Our first speaker, Viktor Potabayev, with co-authors, and the name of the title of the paper is "Leads in the Ice Cover of the Arctic Seas and the Ability to Predict Their Characteristics Based on Satellite Data." So Viktor, are you ready to start?
I'm ready.
Okay, take it away. You have 20 minutes altogether.
Наверх.
Совместное использование. Совместное использование. Вот. Теперь нужно включить F5.
Так, что там?
Вот, значит, здесь тыкнуть. Вот, показ слайдов.
Не-не-не, в Zoom войдите.
Не надо в Zoom, вот здесь показ слайдов. И сначала.
Так, а говорить я могу?
Да, теперь можете спросить, видно ли?
Где эта презентация?
I may begin?
Yes.
Zoom войдите.
Да, все в Zoom.
Good afternoon. Excuse me. I don't know English well. I use translator.
Приготовились? Листайте.
The discontinuities in the sea ice cover, which are also called leads, are a characteristic element of the ice cover structure in the Arctic seas. They are presented as cracks, canals and fractures with open water or young ice. Their length can comprise several hundreds of kilometers and more. The lead's width varies from fractions of a meter to 5 to 10 kilometers. Practical interest in leads is caused by their possible use in navigation. It is known that when navigators use leads, the orientation of which deviates from the ship general course by not more than 30 degrees, the motion speed increases 1.5 to 2 times. Being potential routes of easier navigation, leads are used for escorting of transport ships by icebreakers in the winter-spring period in the Arctic sea sand during voyages of icebreakers in the Arctic basin. Satellite images are at present the main source of data on discontinuities in the ice cover. The main advantage of the space survey is a high range of vision, i.e., coverage by one image of the surface of a large area. We make decoding and digitizing of leads on satellite images by means of GIS ArcMap. In the course of processing of each image, one records on it the geographical coordinates of the end of each relatively rectilinear segment of the lead, i.e., the lead segment within which its orientation does not visually change. The results are entered into the electronic archive of leads. which serves as initial data for subsequent calculations of their characteristics. We use modal orientation as the characteristic of the prevailing direction of leads. The modal orientation of leads presents the direction at the range of plus or minus 20 degrees from which the total length of leads in the square is the largest. The range itself is called modal at this. The ratio of the total length of the leads, the orientation of which gets into the modal interval, to the length of all leads in the square is called the exceedance probability of the modal interval. This value characterizes the degree of stability of the prevailing direction of leads and is expressed in %. As a characteristic of the density of the location of discontinuities in space, we use their specific length. For the Laptev and the East Siberian Seas, both of these characteristics are calculated for 100 times 100 kilometers grid squares. Figure presents an example of the results of decoding and digitizing a Suomi NPP image to determine the characteristics of leads in the Laptev Sea. The modal direction of leads is presented in Figure C by the correspondingly oriented segments, the length of which is proportional to the exceedance probability of the modal interval. The specific length of leads is presented in Figure C by numerical values. The possibility of planning the optimal route of navigation of ships in ice taking into account the en route discontinuities determines the demand for the forecasts of prevailing orientation of leads and zones of their formation for navigation at the Arctic seas in the winter-spring period. The aim of this study is to develop a method of forecasting the prevailing orientation and zones of formation of leads in the Laptev and East Siberian Seas. The air flows influencing the ice cover form the ice drift fields. The non-uniformity of the ice drift velocity drift creates zones of pressure and diverging in the ice cover, where leads are formed or close. Wind depends on the atmospheric pressure gradient, and therefore the pressure fields are a primary predictor for forecasting the lead characteristics. At the changed wind direction, modification of the systems of leads in the ice cover occurs. The direction of leads and their specific length change. The analysis of the surface pressure fields. Ice drift and systems of leads shows the dependence of the direction of leads on the atmospheric pressure field and the related ice drift field. As an example, the figure shows the atmospheric pressure, ice drift and leads in the ice cover for the 29th of December of 2017. The atmospheric pressure gradient was large, which determined a large speed of the southwest wind above the sea area and as result intensive ice drift. The number of leads for this date in the Laptev Sea is determined by a large non-uniformity of the ice drift velocity. The drift velocity increases both from the west to the east and from the south to the north of the sea. Correspondence between the ice drift direction and the orientation of leads in different parts of the sea is different. In the western part of the sea, there are cases where the orientation of leads differs significantly from the perpendicular one to the ice drift direction. The use of natural connections between the atmospheric pressure fields, ice drift and divergence of its velocity and the characteristics of leads in the ice cover make it possible to develop an analog method of forecasting of leads characteristics. The essence of the analog method of the forecast is the choice by retrospective data of mean daily fields of atmospheric pressure, which within the study area have the maximum similarity by structure with the prognostic one. Such similarity suggests coincidence of the direction of air flows and the pressure gradient values and similarity in the location of zones of increased and decreased pressure and coincidence of the centers of cyclonic and anticyclonic circulation at their presence in the seawater area. If it is not possible to find in the electronic archive the atmospheric pressure field, which could be similar to the prognostic one within the entire sea. The choice of several fields, each of them corresponding to the prognostic one only in one sea region, is possible. In this case, the final analog is formed as a mosaic of the chosen fields. One adds to the actual surface atmospheric pressure field the calculated for the same date fields of ice drift and divergence of its velocity, and also information on leads that existed in the ice cover during this period. A set of these data presents one complex analog. The fields of modal orientation and specific length of leads are a composite part of each analog. During forecast preparation, one considers as priority data the data obtained from the electronic archive, i.e., actual data from the satellite image. In the case of absence of initial data on some squares due to impossibility of decoding the discontinuities as a result of cloudiness, one can use as their prevailing orientation the calculated direction of the small axis of the ellipse deformation rate. A set of complex analogs formed for the specific sea serves as a basis for issuing a forecast of the characteristics of leads by the considered method. At the successful selection of the analog to the prognostic field of atmospheric pressure, it is supposed that the characteristics of leads from this analog will be similar to the prognostic ones. Based on the values of the drift velocity divergence in the analog, zones of expected formation of leads, divergence is positive, and zones of compression, divergence is negative, will be determined. The high accuracy score of short-range forecasts of the fields of surface atmospheric pressure allows us to hope for the minimal number of unsatisfactory forecasts of characteristics of leads due to discrepancy of the prognostic pressure field to the real one. By the present time, several dozens of complex analogs were formed for the LAPTEF-C, resulting in preparation of 2 diagnostic forecasts. The corresponding field of one of the available analogs was assumed to be a prognostic field of atmospheric pressure, while the other served as data for making the forecast. In the first forecast for the baric field assumed to be prognostic, it was possible to choose 2 analogs. Figure represents the atmospheric pressure fields with one of them assumed to be prognostic, and 2 other fields were analogs to it. The field in Figure B was assumed to be an analog for the northern part of the sea, and in Figure C, for the southern. The division when using the first and the second analogs is shown in Figure A by a dashed line. In each chosen analog, the squares located within the zone of correspondence of its atmosphere pressure field to prognostic were marked. By these squares, the values of modal orientation and specific length of leads were calculated. The values of these characteristics of leads were calculated only using the actual data obtained from decoding satellite images. The calculation of prevailing orientation of leads along the direction of axes of deformation ellipses of the ice cover was not used in this forecast. In this connection, not all squares of the chosen grid were provided with data. In order to be able to assess the accuracy of the prepared forecast, it is necessary to compare the values of characteristics in the chosen squares of the analogs with the values in the corresponding squares of the analog taken as a prognostic. A total of 38 squares were analyzed. In 26 of them, the differences between the prognostic and actual values of modal orientation were not greater than 30 degrees. That is, the assess of accuracy of the forecast of the prevailing orientation of leads was 68%. In order to assess the accuracy of the forecast of location of zones with formation of leads, squares were identified on the chosen analogs, in which the highest values of the specific length of leads were noted. In the analog for the northern part of the sea, 4 such squares were selected, and in the analog for the southern part, 5. All these squares except one were located in the zones with positive values of divergence of ice drift velocity. And the specific length of leads in them was 3.5 times higher than the corresponding value in the rest of the squares. The specific length values in the identified squares were compared with the corresponding values in the analog assumed to be prognostic. Of 9 analyzed squares, data on leads in the prognostic analog were absent in 1, in 6, the specific length values were overestimated and in 2, underestimated. Thus, the exceedance probability of the forecast of the zone of formation of leads can be considered equal to 75%. When preparing the second diagnostic forecast, it was required to use 3 analogs. Of 34 squares provided with actual data on leads, on the selected analogs the permissible value of 30 degrees was not exceeded in 25 squares, i.e., in 74% of the cases. In each of 3 selected analogs in the zones of correspondence of their atmospheric pressure field to the prognostic one, there was present by one local area with the positive values of divergence of ice drift velocity. All 3 areas were fixed on the prognostic analog, although the sizes of zones slightly differed. Unfortunately, data on leads were available only in one of them. But the values of the specific length of leads within it were higher than in the adjoining squares.
Conclusion is on screen. Please read.
A further increase in the number of complex analogs will help to improve the accuracy of forecasts of the direction of leads and of the zones their formation. Thanks for attention.
Okay, Victor, thank you very much for presenting an interesting piece of work. We're now open for questions. We have a few minutes on the schedule, so we'll see if there's anyone in the Zoom meeting have a question or comment, and then we'll see if anything comes in from the YouTube feed.
Я поняла, что есть несколько вопросов.
То есть, а как это видеть?
Sergey, do we have anything coming in from YouTube?
To read from YouTube. So we should, I guess, YouTube загружен. We don't see YouTube.
No, Sergey will tell us if
question.
there's a question from YouTube.
No, we have not.
But I'm not seeing anything come in. Well, I'm curious, could you say something, Victor, about the time it takes to update the forecast? I'm wondering specifically if, operationally, if it's a fast operation, so someone aboard ship could, look at the predictions in a timely manner, quickly.
Это быстро используется при навигации, я так понимаю, да?
Речь идет об обновлении
Речь идет только о возможности создания прогнозов. Пока не используется.
Речь идет об обновлении. Как вы обновляете эти прогнозы?
Скажем, настоящий прогноз еще не составляется, это только попытки его составить.
So at the moment, these forecasting are not working yet. So this is just a project. So we just try now, but we don't use it still.
Okay, understood. I didn't realize. So it's still in the development stage.
Yes, it's in the development.
Very good. I know these things are a very important issue nowadays, so it looks like a great project. Do we have any other questions? I guess not. I don't see anything coming in on the chat. Okay, well, that is about our 20 minutes. Victor, thanks again for your very nice presentation, and we'll move on. It looks as if Oliver Damon is logged on. Are you with us, Oliver?
Yes, can you hear me?
Yes, I can. Good. Okay, so he'll be presenting a talk entitled Applications of Radar Interferometry for Measuring Ice Motion. And it looks as if Sergey needs to switch the screen over. All right, we're headed in the right direction.
Let's see here.
And you'll have 20 minutes for the talk, including questions. And so your time, if you're ready to start.
Yeah.
It looks as if you are. Okay, go ahead. So let's welcome Oliver Damon to the session. Go ahead.
Thank you so much. Yeah, hey everyone. A few of us at University of Alaska Fairbanks at the Geophysical Institute, and also some colleagues at Chalmers University have been working for a few years now on applications of radar interferometry for measuring ice motion. And I think some of this might have quite promising applications for what this audience is working on as well, in terms of understanding more sort of structural interactions, ice engineering, and so forth. So that's why I think this might be interesting. And we have, sort of our main findings, I guess we can sum up to, is that we can derive very high accuracy ice motion on timescales from sort of milliseconds with these ground-based system, as we see an example of here, to the order of months with satellites. And we can use this to map deformation, stability, and also say something about fracturing, and as well as vertical displacements from tides. And using sort of these ground-based systems, we can track speed and continuous deformation of drifting ice. As we looked into a few different, let's see, how do I, yeah. We looked into sort of a few different ways of doing this. First of all, here's sort of a schematic of coastal sea ice, where we have a changing stability with an increasing stability towards the shore. We have the bottom fast ice zone with where the ice is not free to move at all, as it's frozen to the seafloor. And then we have also severely stabilized ice by either barrier islands or in the lagoons, where the ice will predominantly sort of be impacted and move a little bit in terms of, or due to thermal creep and cracking. And then we have sort of floating ice that is stabilized by ridges, where we also can have some dynamic deformation, and then more sort of more free to move floating extension to this landfast ice. And so this enables us to, the first thing we did was to use interferometry from satellites using repeat pass, where we use one image from a satellite, and then the next time the satellite passes overhead, we get another image days to weeks later. This is possible to use this approach for landfast ice, but the drifting ice will move too much in between these satellite overpasses. And this is where we've used sort of these constellation or tandem systems, where you get two images quite close in time. The problem with that is that we have sparse data availability with these tandem constellations. So to look at drifting ice, we also our third example that I'll show you is using a ground-based system mounted directly on the sea ice itself. And we also sort of the force application is using this for mounted on a building and rotating, scanning a section of the landfast ice. And in essence, though, the satellite-based approach gives you large spatial scale, but a limited temporal coverage, and these ground-based systems give you a high sampling, but at the same time, a limited spatial coverage. So just quickly, in terms of the technique of radar interferometry, as a conventional radar and how we think of ship radar and so forth is evaluating the backscatter return and the strength of the signal from different scatterers. Radar interferometry utilizes the phase information of this electromagnetic signals, showing here how the phase of the signal sort of propagating down towards the ground from a satellite. And if we have two satellites that are separated, it has two acquisitions that are separated in time. One can be, for instance, days later. Then if we subtract the phase information from these two from one another, then the changing phase will be directly related to the motion on the ground and between these acquisitions. And this phase we can view that as sort of these stripy patterns, and where the sort of the density or the spacing between these stripes are indicative of the motion. So first of all, what we can see, this is now northern Alaska with Utqiagvik near the northernmost point here, all the way down to, excuse me, down to Prudhoe Bay. And first of all, what we see is where we have these stripes, so this phase change response at all is where the landfast ice is. And so we can sort of use this to track the landfast ice or delineate it. But what we also can do is to say something about how fast the ice moves. And in particular, we can see these stark gradients here, where you go from this very high fringe density to a much lower fringe density, as we call it. And this is directly where there's a line of grounded ridges. So we can use this to identify where these grounded ridges are, as well as say something about how they're stabilizing the ice cover. And then much closer to the coast here, we see some areas where there seems to be very little change at all, particularly here in the Colville Delta. And one example is here near the Ugruk Island, which is a man-made island for oil and gas exploration, with an ice road connecting this island to shore. And what we see is that we can use this technique to basically establish where there's no change at all, this purple region, which is where the ice is bottom fast. And this is of interest because you go from sort of a risk of fracturing the ice and so forth from these construction vehicles, except for on bottom fast ice, where you reach sort of a near infinite load bearing capacity. So here we can directly see with this technique that part of this ice road goes across floating ice and a part across bottom fast ice. And this is also of interest in terms of the Ugruk Island had to be constructed with transportation strictly across bottom fast ice. And so this technique then enables us to delineate or map sort of these different stability regimes. We can also say something more quantitative as well. This is showing the North Star Island ice road extending from shore to the North Star Island ice road. This is showing the backscatter imagery with where we can see some darker areas, which is associated with smooth ice, and some sort of brighter, more deformed ice. And what we can do is that we can use this phase return for directly derive the strain of the ice, and also use that to calculate or estimate the amount of stress that we would assume in the ice if we didn't have any fractures. And what we see is that this stress would be far greater than an expected yield stress, and we can use that to similarly sort of estimate the number of fracture events that we might expect. And so for that, we can also back out sort of the relative amount of fracturing and relative stress in the ice. And we see that basically along the beginning and the end of the ice road, as well as this central section, is associated with more stress and fracturing, and particularly the central region too, around mile marker 4.3, which is known by engineers to cause heavy fracturing. So this might be a technique that might be useful for sort of guiding additional surveys and so forth to see where we might benefit from more repairs and so forth. And then we looked at this tandem constellation that I mentioned, where we can basically through an instant of time get the drift speed. And so this is in the Vilkitsky Strait on the Northern Sea route, where the ice is in this instance drifting from west to east, and we see as it rounding the Cape, it breaks up. This is another backscatter imagery, and it's difficult to see anything more from this in terms of the drift. But if we look at the interferometric derived drift speed, we can basically identify near stationary ice close to the coast, as well as closer to these islands. And we can also identify sort of intermediate zone of a little bit higher drift speeds, as well as the central channel, which shows a variable drift speed as it's getting closer to the Cape, and as it rounds, excuse me, changing the drift speed as well. And this is causing a convergence here. And as there's a lack of any sign of this convergence or ridging in the backscatter imagery, this looks like to be an entirely transient feature. So this might tell us something about ice conditions and ice dynamics, but in terms of the sparse data availability, this potentially limited use, at least at this point for operation. But this is where we also used a ground-based system that we placed on a multi-year ridge in the Beaufort Sea, and we basically stared out, getting a return signal from different ridges and ice features away from the radar. And we stared out and sampled continuously the distance to these objects at about 500 hertz. And what we see over this is just an example of over 30 seconds here. We see that over these 30 seconds on the x-axis here, these different points approach the radar at different rates, where we have most movement further away because it's further between the radar and this point. Here is indicative of a near uniform convergence of about 10 to the -7, which is a typical strain rate in the Arctic Ocean. It also allows us to remove this general uniform convergence and look at a residual strain if we remove that. And over this 30 seconds, we can also see that now we're down to the sub-millimeter scale. What we can see here is that the points that are on multi-year ice are moving slightly different than the points on first-year ice, which indicates that this potentially can be used to discriminate different ice regimes. The last example is where we use this system to and basically stationed it on top of a building in Utqiagvik, similarly looking out over the landfast ice. And now, not over 30 seconds, but we had this acquired data over almost 24 hours. And the signal now, as this system is quite high up, is sensitive to both vertical and horizontal motion. And so we looked at particularly a point close to a grounded ridge where we expect very little lateral motion to occur. And we see that the derived vertical motion is sort of a cyclical nature and matches very well with the modeled maximum and minimum tides. So this seems like potentially an approach that can be used to look at tides and storm surges and so forth, which is related to, has shown to be related to breakout of landfast ice. So what we wonder is if this system can potentially be used as an early warning system for ice breakout and so forth. We can also use this to look into stretching of the ice as the wind, in this case here in this gray line, veers from alongshore to offshore, reaching up to 7 meters a second, and how these individual points is stretching away from the coast at a few millimeters over these 24 hours. And yeah, so to conclude some of this, we can use, of course, satellite and these ground-based system. They're very portable, just like this one. You can basically set it up anywhere you have some solid platform to work from. And the satellite-based interferometry can be used to monitor millimeter scale landfast ice dynamics and stability over tens to hundreds of kilometers and over months potentially. And ground-based interferometry can be used to monitor continuous tidal motion and deformation, which might have potential value near operations, and particularly the stare option, to stare in one direction at a sampling of 500 hertz enables instantaneous drift speed tracking, potential discrimination of different ice types, which might have applications for looking at loads on structures, for instance, by resolving sort of very high accuracy ice drift. That was all I had. Thank you.
Okay, great. Oliver, thanks so much for a wonderful presentation. We have a couple minutes left in our time slot for questions. So as I said before, those of us on the Zoom call can speak up directly. And then if questions come in from the YouTube feed, Sergey will pass those along to us. In waiting for something to pop up, let me ask you, I'm particularly interested in the last topic where you're the land base with this high 500 hertz sampling rate is great. A lot of potential there. One question is, what's the maximum range for those measurements from the land-based system under, let's say, ideal atmospheric conditions?
Yeah, it depends a little bit. You can certainly set it to different ranges. That will sort of depend on what you pick up, and you might have. It depends a little bit as to how rough the ice is and so forth. But in general, we have been looking at a signal and consistent sort of usable signals out to about 4 or 5 kilometers.
Ah, great. All right. So, but it strikes me that if you had a real stable ice cover and you wanted to study things in detail. You can actually put a reflector out, you know, in terms of a radar target, basically to monitor specific locations, right?
Absolutely. So that's something that you can do, that would enable you to sort of get the deformation and motion of particular places of interest. As we have done, we've sort of used a little bit these ridges as a reflectors, so to speak, and looking at the movement of these sort of the rougher part of the ice, where in particular.
Oh, we did have a question came in that Sergey just passed along. Stepan Maznev, please clarify, knowing estimated stress, can you identify zones of ice ridging and distinguish them from level ice?
So I guess I'm not quite sure if I understand the question, but
I think it's basically if you're looking at this motion, can you identify zones where ridging is likely to occur or is occurring, as distinguished from level ice?
Yes, so I think so. In terms of what we did here, is probably the closest thing, where we basically derive the stress or estimate a stress from the motion that we observe, and what we identify is areas that are that will have a higher likelihood of having fractures, and that's where you're most likely to get ridges too. So for instance, here where you have the ice road, we can actually see in the interferogram itself that you have this ice road is sort of hampering some of the motion coming across, and seems to actually stabilize a little bit of the ice to sort of the shoreward ice. So we can definitely see that there's more stress in the ice on this western on this eastern side here. And this is also where you can sort of see this in the backscatter imagery as well, that you have more ridging going on.
All right.
But
well, thanks so much. We're a bit beyond our time right now, so we'll have to wrap it up there. But Oliver, thanks so much for a very nice presentation, and give my regards to a couple of your co-authors. I've done some work in Northern Alaska with Andy and Hayo many years ago. Okay, so we'll then move on to our third and final talk, being presented by Valeria Selyuzhnok, Landfast Sea Ice Edge Mapping from SAR imagery. So Valeria, are you, there you are.
Yeah. Hello.
Great. So yeah, welcome to the session, and you have 20 minutes, including some time for questions. So go ahead and start.
All right. 1 second, I just have to figure out how to share the presentation.
You're on the screen, so I think you're good.
Okay, so can you see it?
Yep.
Oh, all right.
Excellent.
So I'm going to present another new method for landfast sea ice mapping from SAR imagery, from C-band SAR, and this method we developed together with a colleague of mine, Denis Demchev. So there are actually quite a few methods to map landfast sea ice. And for operational purposes, the experts do it manually. So they look at the time series of images, and based on what they see, they draw the edge between what they decide is motionless landfast ice and what they think is drifting pack ice. It can be quite simple, like on this Envisat SAR image, where landfast ice is kind of separated from pack ice area by a narrow lead. But sometimes it's not that trivial. And there are also semi-automatic and automatic methods to map landfast ice, and they rely on the fact that the surface area, the surface properties of a landfast ice area are not changing in time compared to the properties of the surface covered with pack ice. So when pack ice drifts, for example, here's probably dark part is a level ice. It's here now, but in I don't know, 10 hours it drifts away, and then the surface properties here are different to what we observe on this image. And there are many techniques to emphasize this difference between constant and changing surfaces. These are image cross correlation, gradient difference, composites, and even Oliver just presented applications of interferometry to map landfast ice. But we introduced a new method. We suggest to use the direct criteria of immobility to map landfast ice, and this is a drift speed. On this image, you can see these colorful vectors. They indicate the sea ice drift speed, and well, over the landfast ice area, there are some dots which are not quite visible, but they indicate no speed, no drift detected. So area with no displacement is landfast ice or land, and area covered with the vectors is pack ice. We use a fine resolution ice drift product. The algorithm looks a bit difficult, but what is important here is that we combine two common techniques to detect sea ice drift. First, we calculate sea ice drift using feature tracking, and this gives us the first guess of sea ice drift. It's it's highly reliable, but the problem with this is that it's not. It can be, well, it's not on. Well, the coverage is sparse, yeah, let's say. And then using this sea ice drift as a first guess, we apply cross correlation, which provides us with more sea ice drift vectors. And as a result, we get the fine drift product with resolution, for example, from Sentinel-1 extra wide swath data with 40 meters pixel, we get a sea ice drift vector every 800 meters. And then here we get this, the result of the drift application. We get the displacement on a regular grid, and we just select those grid cells which showed no zero displacement. These zero displacement cells then are wrapped up in polygons by special clustering, and at the end we get landfast sea ice polygons. I will show the output of each of the steps. Here you can see the sea ice drift field with the arrows indicating the drift, and next zero displacement points are selected in yellow, and finally we draw the edge in blue using alpha-shape special clustering. We set the parameters for clustering, and we set fixed parameters for clustering. We just define it once. To validate our results, we calculated, we derived fast ice edge for the Laptev and East Siberian Sea from Envisat SAR images with 150 meters resolution, and for the East Siberian Sea from Sentinel-1 data with 40 meters resolution. We compared our edges to those derived by sea ice experts at the Arctic and Antarctic Research Institute. The operational CI chart from the Arctic and Antarctic Research Institute is shown in pink. This is the fast ice edge from the expert, and blue is the fast ice edge derived by our method. Overall, we compared about 20,000 kilometers of fast ice edge. To do so, we measured the distance between the edges every 10 kilometers of the derived fast ice edge. And the histogram shows the distribution of the distances. In case when our fast ice edge was closer to the shore, the distances were set to negative, which means that we somehow underestimate fast ice extent. And in the case when our edge was further away from the shore, like here, the distances were set to positive values. Well, the mean absolute distance is around 13 kilometers, but the mode, which is located at about 40%, so in 40% of the cases, the edge was within, our edge was within 10 kilometers away from the edge from operational CS charts. Our method slightly, well, it tends to slightly overestimate fast ice extent. So here the cumulative frequencies of positive edges are higher than those negative ones. Yeah, and also I have to say that during the preparation of this talk, I found out a bug, and those distances, as you can see from the map, they're actually not the closest way from one edge to another. So actually the method, our method performs better. It should be better than you can see from this data. Also, due to high resolution of the output drift product, we are able to detect stamukhi or large grounded sea ice features. Here you can see the maps of fast ice development from beginning of December to the end of December 2013. And our method constantly detects grounded sea ice features over this area, here and here in the center. And for some reason, the sea ice expert didn't map these features. So probably they are too small or invisible for human eye. However, they play an important role for fast ice development. As you can see at the end, fast ice develops exactly around these grounded features. And so this method somehow reduces the subjectivity to define fast ice edge because it's yeah, it based on the fixed parameters of sea ice drift. And to sum it up, we developed a new method which uses direct criterion of immobility, sea ice drift. This method locates fast ice edge within 13 kilometers at least from the edge located by sea ice experts manually. It can be a source of additional information to map large grounded features. And we suggest that the method can be used as a tool for sea ice experts as it reduces the subjectivity in defining land fast ice edge. This is
Great.
it.
Well, thank you so much. It was a very nice talk and very well organized and on time. So we appreciate that. So we do have plenty of time for questions. As I mentioned before, the YouTube viewers can submit via the chat section there, and those questions will get passed along by Sergey and hopefully pop up on my screen. And then those of us in the Zoom session can ask directly. I do have waiting for things to show up. Could you say something about, let's say through a season, how dynamic is the edge of the landfast ice? Is that sort of in need of daily or weekly or monthly updates in order to keep it current?
Yeah, so, well, operational maps are issued every 7 days. And during the development of fast ice, actually, it can develop quite rapidly. And for example, here, if you look at the pink color, this is a fast ice mapped by the experts. And this is a huge difference between 2 dates. So we look at the shorter time interval. I forgot to mention that the blue dates corresponds to the date of the pair of images we process. So we look at the changes over 3 days over here on the central image, and compared to well, to the one to the left and to the right, these are huge difference. So you can during the development of fast ice, you can see changes in like a couple of days.
Yeah.
I don't know if it was your question or.
Okay. No, thank you. That's great. And we just had a question pop in from YouTube that Sergey passed along from Tom Zagon. What is the min-max time between image pairs?
Well, the is 1 day that we were lucky to get such an image covering the same area just a few hours apart. The maximum is actually, well, it depends on the definition of landfast ice. You can use a pair with a difference of 20 days, but then you won't see the drifting ice. You will see only stationary points, but it will be a mean picture of fast ice, a mean situation over this 20 days. In our study, we use the pairs with a difference from 1 to 7 days.
1 to 7 days. Okay.
Yeah, but this was made just to have comparable results with the operational sea ice charts.
Yeah,
you can well use any time difference depending on how you define landfast ice.
Okay, very good.
Hey,
Thank you. Do we have any other
Is
questions?
there time for another question?
Yeah.
Yeah, great talk, Valeria. Really enjoyed it. I wondered, you were alluding to these discrepancies or through this validation process. Do you have a sense of sort of, is there like one particular reason why these, why you get large deviations? I'm wondering, like, if, for instance, you might be mapping, since this is sort of based on drift, that you have, if you perhaps measure or map sort of stationary ice that isn't considered by, ice charting people to be land fast, but it's perhaps really your algorithm that does a good job to map stationary ice, but it's not land fast or something like that. Could you say a little bit about that?
I'm not sure I understood your question. So
No,
you
sorry. Do you know sort of why there are discrepancies between? I mean, no automatic approach is perfect, but is it like a particular? Could it be mapping stationary ice, for instance, that isn't land fast, or does it fail in some particular cases, or?
Well. For of stationary ice, because we know the region, we know that. Well, can you hear me? I have some problems with.
We can hear you now.
Okay.
You froze
Yeah.
up for a second there.
Okay. So for this particular case, we are sure these are stationary parts of sea ice, which is not because we know the region and they're located at the lower depths, so they're quite likely grounded. But for other cases, well, I haven't seen anything like this for other regions. I mean that probably at some point our algorithm fails and it shows something wrong, but we haven't encountered such features somewhere else.
Okay. Great. I think unless there's a real quick question, I think we're a little bit over time, so we should wrap up the session now. But I would like to thank our three authors for some wonderful presentations. You folks were all superior organization and presentation skills. So thanks so much for your work there. And so with that, we'll close the session. I believe it's time for a lunch break, at least in some of the time zones. And thanks so much for your attention. I think the YouTube feed will be, you can play back our session for the next 24 hours. So if somebody does want to catch any of these talks, you could pass that information along, any folks that missed it. But thanks again, and hope you enjoy the rest of the meeting. Signing off now. Bye.
Thank you, David.
Thanks a lot, Sergey. Nice job on everything. Worked well. Thank you.
Добрый день.
Добрый день.
Я вот технический, собственно, ассистент.
Ага, Федор, да?
Вот. Ну, сейчас у нас пока только Писарев подключается, это третий доклад, ну, вернее, в зале ожидания. Сейчас тогда ждем, наверное, остальных и их запускаем.
Мгм.
Вопросы, которые на YouTube в чат задают, я тогда буду вам в Zoom в чат скидывать, чтобы вам не лазить между двумя
Хорошо, да.
сообщениями в Zoom. Ну, вот.
Мгм.
Хорошо. нас есть 3 докладчиков из 4. Я думаю, мы можем их приглашать уже сюда, чтобы они готовились.
Да, хорошо.
Здравствуйте, коллеги.
Добрый день.
Добрый.
Осип, у нас пока у Насти, там, у Магаевой проблемы какие-то с электричеством, интернетом, поэтому она, может быть, и не успеет вовремя подключиться.
Угу. Тогда мы ее будем ставить на потом.
Ну, наверное.
Коллеги. Добрый день.
Добрый день.
Добрый. Добрый.
Осип, у нас пока у Насти, там, у Магаевой проблемы какие-то с электричеством, интернетом, поэтому она, может быть, и не успеет вовремя подключиться.
Угу. Тогда мы ее будем ставить на потом.
Ну, наверное.
Коллеги.
У кого-то работает трансляция в YouTube одновременно с Zoom. Ее транслируют повторно с запаздыванием. Надо YouTube, наверное, выключить.
Да, или просто там звук в трансляции отключить, если вы хотите одновременно. Я думаю, нам пора начинать.
Okay. Good afternoon, dear colleagues and participants of POA conference. Today we were on the session which called Dangerous Hydrometeorological Processes and Phenomena. And my name is Osip Kokin. I will be lead this session. I'm from Moscow State University, Geography faculty. And our first presentation will be given by Stepan Maznev. So please, Stepan, you can start your presentation.
Can you see my presentation?
Yes, we can see your presentation.
Okay, I'll start now. Thank you for introduction. My today's presentation about Tulenny archipelago of the Northern Caspian, also known as Seal Islands. And we will discuss the ice gorging processes that are acting here every year. The Caspian Sea is the largest brackish lake in the world, and its shallow northern part freezes annually due to unstable hydrological regime in the cold season. The ice conditions of the northern Caspian, the ice area, thickness of the ice, ridge concentration, they are characterized by significant interannual variability. Maximum ice extent can reach Makhachkala and Aktau. In the middle Caspian, ice appears along the coasts, and in the southern part, there is no ice at all. Here you can see the satellite image of northern Caspian, and here are the Tulenny Islands. You can see that they are on the southern boundary of the ice extension. The first who considered the effect of ice on the seabed on the northern Caspian was Boris Kosechkin. He found out the traces of ice impact of moving ice pileups, as he called them, plowing scars, in the area of Tulenny archipelago. He showed that ice hammocks with a 35-40 centimeter sail has a keel about 3 meters, which exceeds the prevailing depths in that area. The depths here are from 1 to 3 meters. The analysis of the distribution of main scours direction showed the similarity with the directions of prevailing winds, and he proved that the movements of pilot ice is subjected to the prevailing winds and currents. Here you can see modern studies of ice on the northern Caspian from our colleagues and sponsors of this conference, Iceman.kz. They make a comprehensive monitoring of ice drifts, Tamuk distribution, and other ice parameters. The studies throughout the northern Caspian are based on continuous monitoring and hintcast, and they use mainly synthetic aperture radar images from Sentinel-1 and for Tamuki deciphering, and Sentinel-2 and Landsat high-resolution cloudless images to confirm the widths of Tamuki and other. So what is the motivation of this presentation? I'm the geomorphologist, and I'm studying the ice scours and their parameters, and we can now conduct the modern study of ice scours, and moving ice and Tamuki are geological agents here. So the question is, how could we combine these studies, how we can use information from satellite imagery, and how can we use information on ice conditions and features together with seabed topography studies. So the goals of this study are to perform a detailed study of ice covers using satellite images and fieldwork, and to show that the Tuoleni Islands can become a testing ground for studying of the seabed gorging by ice features. Our methods for scour deciphering, we use visible wavelength imagery from open sources, Yandex Maps and Esri World Imagery. They provide world view images with 1 meter size pixels. We manually determine ice cores and determine their widths. Then, by the code developed for Python console for QGIS to define the length and direction of these lines, and at the end we have a picture like that. This is ice scours and the lines of deciphering and the attribute table with all the parameters. During field work, we used the camera GoPro Hero for underwater shooting, Lawrence Mark 5X sounder, GPS, and a laptop with a high-pack software package to record the results. We came from Bautina to our area of fieldwork and conducted 5 Ehud sounding profiles and underwater shooting. We moved with a motorboat like this, and here you can see how the Tuoleni Islands look like, and you see that the depth here is depth allows to just walk by feet on the seabed, and here is me. Our results. First results of remote study. The width of ice cores on the site ranges from 11 to 325 meters, and on the average have 39 meters. Scours are from 2063 meter to more than 8 kilometer long, and have at the average about 1 kilometer. Combs consists from 3-5 scours and have an average width of 3,000 meter. In this case, length and width of the single scores are slightly larger than the lengths of and the width of scores from combs and systems. There are more single scores than combs, and scores are generally have direction from west-northwest to east and southeast, how you can see on the rows diagrams, which corresponds to the main directions of winds. Scores of the medium length and the medium winds prevail on the side of deciphering, and the estimated coverage of the seabed by landform of ice impact is about 60%. The results of Ehud sounding show that the scours have width from 50 to 150 meters, gently sloping size, and the depths of from 20 to 60 centimeter, and the average 30 centimeter. The height of side berms is less than 20 centimeter, but their width is about 10 meter. Here you can see the example of underwater shooting of the ice scour. They often have a complicated shape W shape and several local ridges in the central part. For example, you can see here on the satellite image and on the echo sounding profiles. In fact, such scores are merged combs with residual ridges in the central part, and precious ridges are also expressed well and composed of a mixture of algae and silty soils of the upper part of the sediments. Here you can see other look of the ice impact on the seabed. Discussion of previous studies of the Northern Caspian seabed show some results for comparison at depths from 3 to 12 meter in the area of the Filanovsky-Kachagin fields. The width of ice cores is up to 5 meter, and the width of system is up to 200 meter, and the length is more than several kilometers. Koshechkin showed for the area of Tuleni Islands that the length of plowing scores are from 2 to 3 kilometer, and he argued that the depth is only 3-4 centimeter relative to the bottom surface, and with the algae cover gives 7-15 centimeters. At all, it gives about 20 centimeter depth. At Kashagan fields, we can at the Kashagan field we can see that the maximum width is 77 meter and more than 1 meter depth of the ice cover. The greatest depth of Stamuka pits in this same area is about 1.2 meter. In the area of the Northern Caspian, it was shown that the depth of scours is 10 centimeter, about 10 centimeter, and you can see that this study shows that the length is about on the average, but the width is more than in other studies, and so some parameters are the same. So we believe that the Tuleni Islands can become a testing ground for the study of the ice process and the effect of the seabed and morphology of ice cores. Here we can see some Stamuki of the each season, and taking multi-year imagery, we can estimate the exact scores that was made from exact ice features. That is our goal for next period. This data set shows that every season have its individual places for Stamuki forming, but we see the traces that are made of not of Stamuki, because Stamuki don't move and they make Stamuka pits. The traces, the scours are made by moving ice ridges, but they are not so easy to decipher from images, and this is work for the next period. So here I want to show you some starting studies with colleagues from Iceland and with colleagues from Southern Scientific Center. So we estimated some zones of ice impact on the whole Caspian, and how it moves with the temperature and sea level variations. And another study shows that severity of winters have a great impact on the location of ice impact zones. So in the end, I want to say that using multi-temporal imagery, we can study every ice formation that comes ground and estimate its motion before grounding. So I believe that in the next step that we can find the scour that made by this ice feature and define its parameters. And the Tulane Islands are the rare place with the unique conditions where such study is possible, because the scours are not destroyed by waves like in the most part of the Caspian Sea. And the development of the technology for the comprehensive study of ice gorging in the Tulane Islands area can give new results and bring us closer to understanding of ice gorging processes at all. Thank you. That's all.
Thank you, Stepan, for your presentation. And are there any questions in live chat in YouTube?
No, we have not any questions.
So there are no questions. So should we go to next presentation? And in program, the next presentation should be Anastasia Magaeva, but she has some technical issues and probably she will make her presentation later. So now we can go to the next presentation. Sergey Viktorovich, do you ready?
Yes, I'm ready, but several seconds. I will be here.
Okay. We have time.
Yeah, more or less. Yeah. Where is? Sorry. Can you see my presentation? Yes. Excellent. And then op. 1 second, not work. Okay, let's start. You see, the title of my presentation is Layered or Rafted Ice on the Shelf of Sakhalin Island. And I'm sorry, I would like to move our faces, otherwise I cannot see my own presentation. Sorry. Like this. Okay, on the Sakhalin Island, the problem of identification and a potential threat of offshore structure. I am from Shirshov Institute of Oceanology of Russian Academy of Sciences, and my co-author Alexander Tsvitinsky from Zubov State Oceanographic Institute. So we would like to present you some information related to two big expeditions on a Sakhalin Island. One was carried out in 2016 and other 2019. And you can see the Sakhalin Island shore. It's eastern part of the Sakhalin shelf. And this red line, it's a so-called station. So in 2016, we just go on a ice field and measure a lot of parameter of on every ice field. And let's say that I will say after this ice form, so like in Russia, ледяное образование. So you see this red line, it means when we landing on an ice floe, they drift next time. So line, it means a long line, it means quick drift. Point, it means that ice floe was on a place. The same picture to the another expedition, 2019, and again red point and this line demonstrate position of measurements and what the drift was. And when we measure every ice floe, we carried out a lot of measurements, but now we are interested about some surface topography, thickness of a piece of ice, and then we are interested about some characteristic of the ice floe. I mean some texture of the ice core and so on and so on. So as a result, on every ice floe we obtain the map like this. What we see, this is relief of a piece of ice. You see that it's not so big ice, it's only less than 120 meters. But by the way, it's the biggest piece of ice of the Sakhalin Eastern Shelf in both expeditions. So it's not classical Arctic, Central Arctic ice floe, several kilometers in size. No, it's not so big piece of ice. And we see the surface relief, and like on this map, it's color. And when we look precisely, we can see that, for example, this piece of ice have maximum height of the ridges, something like 1.5 meters. So it's not really rich at all. But later I demonstrate you how interesting such a piece of ice look like. Let's look what we do, our work. We measure thickness using the mechanical drilling, and it's one approach. But then we use some new, for this work, Russian devices, LOZA Georadar, and we measure thickness of the ice, not every 5 meters, for example, but we have line of the thickness. So we measure more or less accurately. In the same time, we take ice core in several places, or each ice floe, and then investigate core and look what's the difference in the different level of this ice core. And some mechanical tests of the every ice core, and imagine that we have, for example, 3 meters of the ice core, and then divided for 10 centimeters, and have a lot of statistics to present what's the difference between mechanical characteristic of different level of every ice floe. And then look what I said before, look how we measure using this georadar, and we obtained such a picture. Look, it's some level of the ice floe, it's some line like this, like this, like this. It's one example. And look, flat ice, and this is the same ice. Look, it's look like flat. But despite the fact that it is flat, it's blue color, you can see more than 7 meters thick in some places. Look, and you see a lot of layers here, and this radar just demonstrates such a picture. But this red line, it's mechanical drilling. And you can see that mechanical drilling, it's not the same like radar, because radar, it's not point. It's some like ball. You measure thickness in ball, not in a point. But the differences is too small that we can use georadar to measure such flat ice flow. And look, even in flat bottom and flat surface, we have 2 meters thick of the ice. It's very strange for Sakhalin, because in this region only 1 year ice exists. Every year ice disappear or melting, and all meteorological condition can under the meteorological condition, the thickness of ice can be not more than 60 centimeters. Okay, 70 centimeters, but it's impossible to have 2 meters of the normal freezing ice with normal condition. So it's a very strange picture, but let's look how many strange we have more. And another job, we use underwater, remote operated underwater vehicles. It's very simple devices, little, it's operator of vehicles, it's vehicles itself. And look what the picture we see beneath the surface of flat ice. We see a lot of layer everywhere. Everywhere we have a lot of layer, and thickness of many years is just the same, 0.5 meters or 60 centimeters and so on. So we see layered ice on the Sakhalin Islands near in all volumetric big in all ice flows that is have big volume. And look, one example for you. When we found everywhere some ridges, here it's something like 3.5 meters high. We understand that if it's this ridges, it's also Sakhalin shelf. And we see ridges and understand that there are keel of ridges. So we understand that it's big volume of such ice. But when we see such piece of ice, look, it's less than 1 meter ridges. It's something like 1.4 meters. And of course, it's a picture from the bridge of our ship. So it's not big piece of ice, but I would like to demonstrate that such piece of ice very dangerous because it's unusual ice. It's the freeboard of this ice flow a little bit bigger than around, distributed around ice flow. So you can understand that, and you have to see this little difference, and you cannot see this difference from helicopter, and you cannot see this difference from airplane, and especially you cannot see this difference from satellite. But when you look closely to this ice flow, you understand that it's something special of that ice flow. And when you really come at the same ice flow that you see in previous picture, and you see icebreaker, this not big ice flow, and look what we see, some layer beneath the ice bottom. And look, this guy come to the shore, and look how it's just here, this same 7 meters that I demonstrated you previously on picture from georadar LASA. And look, it's also 7 meters under the water. So such very strange piece of ice. And when we construct it using surface topography in one hand and georadar measurements in other hand, we can construct more or less precisely 3-dimensional model of ice formation. And look on this, it's the same ice formation, only different angle to look on this ice formation. And you to looking on a scale, you have to understand that vertical scale 10 times bigger than horizontal, just in case. And look, it's the same ridges, 1.4 meters, but ice look like flat, but in the same time, how many layers beneath the such ice, how many layers, and sometimes these layers have 7 meters thick. And it's another example of the same type of ice. Visually, it's the absolutely flat or near flat ice, but it's look like the very unusual. It's big volume of ice due to the fact that all this piece of ice have a lot of layers. It's something like 60 centimeters, 60 centimeters, 60, and sometimes 5 types of layer, the same thick ice layered here. And we not only, and we can determine this not only using the remote operated vehicles, not only using the georadar, but of course using the ice core, and we determine characteristic of ice core, and we see periodic characteristic. I mean, salinity or texture of ice is the same, one level, but later again another level have the same characteristic of salinity, the same characteristic of little bubbles and so on, and the same characteristics of the some mechanical properties. So it's obviously a layered ice, and it's very strange ice because we know that rafting, it's very usual process for young ice. Young, I mean some Nilas ice, dark Nilas or gray Nilas. When young ice, something like 20 centimeters thick, not more, 25, they have rafting like on this picture, simple rafting. Sometimes it's finger rafting when we see this young ice look like such picture. But here we have something that happened with 1 year ice. This 1 year ice have sometimes ridging, but very often rafting beneath the ice. And it's in our expedition, it's not young ice, it's 1 year ice that originated locally and disappear in summer. So hopefully we are not first who just determine such kind of ice. I found in literature something like starting with 1970, we found 10 times in different places of the earth, we found the situation with the same type of ice other people can see. Look, this publication, it's not all publication, but it's the main publication. And how such type of ice can originate? Look like that there are no another places to create such unusual type of drifting ice. It's Sakhalin Bay, where strong tide exists in one hand, and then shore, it's close enough to organize very hot pressure on a even 1 year ice. So it's only one places where strong forces exist, and maybe they can just create such type of ice that then we can see along the Sakhalin shelf shore. And of course, it's very difficult to organize expedition here just to measure this ice in a place of birth, because even here it's very difficult to load instrument on the ice, and it's dangerous enough. And I present such material in different other conferences, and all my foreign colleagues say that it's very strange to go on a piece of ice that have size 100 meters only and drift very quickly. But nevertheless, here it's even more dangerous condition with this huge of tide. But nevertheless, we would like to create maybe some model to try to explain such a phenomenon. But nevertheless, due to the fact that such type of ice is very difficult to determine, it's really dangerous for any offshore construction. And of course, people who know eastern shelf of Sakhalin Islands can ask me why many other expeditions never see before such phenomena. And I have simple answer. Nobody and never go on ice practically. All people look from helicopter quickly or never have so many measurements of one piece of ice. And of course, this piece of ice with such unusual, huge volume, it's a real Sakhalin shelf phenomena, and it's real dangerous for any structure. Thank you.
Thank you very much, Sergey Viktorovich, for your presentation. Have we questions or comments from YouTube live?
May I ask a question?
Yes, of course.
Please tell what is the density, average density of this ice feature? Is it far from the density of the level ice? And what is the ratio between above water and underwater parts of this ice feature?
Density, it's digit, so I'm not remember. We have something like several hundred 10 centimeters part of the ice core, and we have some statistic, of course, huge statistic, but it's the same like any other sea ice. It's not something exclusive. It's some common characteristic for such sea ice. What is interesting that it's one digit, then another, then next 5 ice core 10 centimeters each. And again, first level is the same density like first level on a previous 50 centimeters layer, and so on. So this is about density. About freeboard, or so distance from the water to the surface of ice, I demonstrate you here the biggest difference. It's something like 1 meter. Look, so forget about this rigid part, but look on this flat part, and look that it's 1 meter here. So, but this particular piece of ice you can see from helicopter, of course, because 1 meter you can see. But when you look on this picture, the difference of this piece of ice, it's only 10 centimeters higher than this piece of ice, 10 or 15 centimeters higher. So I can determine such piece of ice only when I stay here and look very accurately around. And then I can see, then we go to this piece of ice, and you understand the ship move all time, and it's very dangerous to go and then lose the ship. You never, it's very difficult to return back. That is why we use a lot of ice anchor here, and all people ready immediately go to the ship when it will be some special voice about this. But look, such piece of ice, look, like this one, it's practically no difference between this piece of ice and that. So difference, it's only 10 or 15 centimeters of this height above the sea. But if you can see this, you never have mistake. You come and you will see layered ice. But I would like to say that our captain worked in this region. He previously was fisherman, and they work here. And only after 22 years to work in this region, he recognized how it's captain have to determine difference between layered ice or rafted ice and simple ice 1 year. So he was very interesting when we demonstrate this 5 meters thick and so.
So the question is, why doesn't it emerge? Why doesn't it flow up and become more, the underwater part becomes lesser and the upwater becomes greater.
Давайте нас почти никто не понимаю вашего вопроса. Еще скажите по-русски, если можно.
Почему он не всплывает?
Но он как раз всплывает, потому что его высота над водой на 10 сантиметров больше, чем вот у этой конкретно льдины. Вот у этой больше, чем у этой. Это можно увидеть только на расстоянии там 200 метров. И то a lot of people from expedition never see this. So you understand how real ice look like, to see difference in 10 or 15 centimeters. Here, no any reason to have flotation. All underwater layer just push up surface not more than 10 centimeters, not more. It's not like ridges. It's only here then flat, and we know that have to be killed here. If it's 3 meters, we can expect something like 14 meters beneath the water. We can expect and we can measure. But when we see flat ice, we cannot expect nothing. We would like to expect that it's simple 1 year ice. In this region, it cannot be more than 60 centimeters in this year, because we calculate through the meteorological characteristics what the limit of the local ice in these particular years. But when we come closely, we determine that this is several layers, and they look like this. And even these three model look. It's when you have real ridge, you see ridge and keel, nothing else. But here, look, it's like block. This part of sea ice, it's like block. It's very unusual. But when you look on a salinity or density, or look on a ROV photo, you found that this not uniform block. It's layers, 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 like this. Look.
Okay, thank you. I understand.
Thank you, Sergey Viktorovich, for your presentation.
Yeah.
So we need to go forward, and the next presentation will be given by Yulia Gleznetsova. Are you ready?
Good afternoon.
Good afternoon.
Can you hear me?
Yes, we hear you and we can see you. Yes, we see your presentation.
Good afternoon, dear participants of the conferences. It's almost night here now. The time difference with Moscow is +6 hours. I present the Institute of Oil and Gas Problems, Siberian Branch of Russian Academy of Science, Yakutsk. For many years, the Institute has been conducting research work on the environmental support of the activities of oil and gas complexes. This work aimed at studying the dynamic of ecosystem remediation, the development of new technologies for the remediation of oil contaminated areas, the study of water and soil hydrocarbons oxidizing microorganisms, and the creation on their basis biological products. The Institute staff annually takes part in the various expeditions, including in Arctic. The socioeconomic development of Yakutia is associated with the production and transportation of hydrocarbons. A practice shows an operation of pipelines is often accompanied by accidental spills. According to the Ministry of Ecology, Nature Management and Forestry, over the past 12 years, the number of oil and oil product spills had amounted to more than 3,016 cases, including the Arctic zone. The nature of the distribution of oil components of the permafrost soil and the level of their impact on the environment differ even in their relatively small areas. The territory of the Yakutia characterizes the widespread permafrost soils. And permafrost conditions, the process of self-remediation of oil-contaminated soils are extremely slow. It is due to a prolonged period of freezing temperatures on the surface layers on the soil, which determines the low flow rate of microbiological processes. The study of the transformation process of pollution and the ability of contaminated soils for self-remediation could give important information for the development of effective methods of cleaning and help maintain the ecological balance of soil ecosystems. Purpose this investigation was study of migration and transformation processes of spilled oil and its futures in permafrost soil on base chemical composition of oil pollution and its changing for 13 years of monitoring results. The object of research was the oil contaminated area at the territory of emergency oil spill at the oil pipeline, which occurred in May 2006. Field walks were conducted each year in summer. 210 monitoring sites were arranged at one of sites located in the influx of stream. 12 test sites in the area were chosen. During all the following years, soil samples were collected from these sites. In this work, complex of physical and chemical methods was used. In this slide, shows the average residual soil content of oil by observation years from 2006 to 2018. As seen, despite of overall trend towards decrease after 13 years of observation, the contamination level varied strongly and remained very high both in the surface layer of 10 centimeters and at a depth 20 centimeters. The maximum decrease twice in oil content was detected at first year of observation. This stage of transformation in soil was mainly due by physical and chemical destruction, gas removal, dissolution, UV destruction. Further, in case of self-remediation of soil, the transformation processes connected with biodegradation of oil hydrocarbons under influence of soil destructors, microorganisms usually joined. In subsequent years, the level of oil pollution fluctuated both up and down. The decrease in the level of oil pollution could be associated with both the process of its transformation and migration with flood, rain, and melt waters. The increase in the level of pollution in the absence of new spills could apparently be associated only with the ability of oil pollution to migrate. All this point to the high mobility of oil pollution in the soils of the permafrost zone. Consider the change of full composition over the period of observations. According to the data on the group composition of soil extract and the type of infrared spectra, oil pollution underwent oxidative degradation process. Over 13 years of observation, changes in the composition of soil extract included a decrease in the composition of hydrocarbon components and increase resins and asphaltants. By the end of observation, the contamination occurred asphaltic resinous composition. The absorption of oxygen-containing groups in infrared spectra of soil extract increased. As seen, the following hydrocarbon groups and bonds prevail in the chemical structure of the extract of contaminated sample collected in 2006 year, almost right after the spill. Compounds with long methylene chains, aromatic hydrocarbons. With time, absorption of oxygen groups and bonds increased in spectra compared by two hydrocarbon structures. Intensity of typical form carbonyl groups and hydroxyl groups increased. There is intensity of bands, methyl and methylene groups, and aromatic hydrocarbon cycles decreased. The process of oxidative destruction of petroleum hydrocarbons are indicated by the spectral coefficients of oxygen-containing compounds. All the above changes in the nature of infrared spectra of oxygen groups compared to hydrocarbon ones was the evidence of oxidative destruction process in soils. According to chromatography mass spectrometer data, all transformation process also characterized by change in the hydrocarbon composition, namely by redistribution of hydrocarbons both inside homologous rows and between different homologous rows. In the initial contaminated sample, and not yet exposed to transformation, prevailing saturated hydrocarbons were alkanes of regular spectra, among which relatively low molecular homologous compounds with distribution maximum NC15, 17 prevalate. This distribution of saturated hydrocarbons is typical for oils of the Vendian Cambrian deposits of Nepsko-Budobinske oil and gas bearing region, where the Tlokansk oil gas condensate field is located. Oil from this field was the source of contamination. It is known petroleum hydrocarbons to have different resistance to biodegradation process. First of alkanes, and among them C17, 18, monomethyl alkanes subject to a process of biodegradation and only then to isoprenoids. As can be seen over time, the content of alkanes 12 and 13 methyl alkanes in the composition of hydrocarbon fractions decreased, while the content of isoprenoid increased. This indicates that change in the individual composition of the hydrocarbon fractions of soil extract occurred under the influence of biodegradation process. Many researchers use a ratio, this ratio is a biodegradation or for determination of oil aging degree. The more intense biodegradation process, the higher values this ratio. Our data over 13 years of monitoring of the area disrupt of the oil spill allowed ELSA to distinguish the main stages of oil transformation in soils. It is shown that the process of biodegradation of permafrost soils under the influence of their own hydrocarbon oxidizing microflora were activated only 2 to 3 years after oil spill. At the same time, for the soils of middle zone, the activation of microflora observed already after 2 to 3 months. Biodegradation process in soil by Kryazon slowed down after about 11 to 12 years. By contamination occurred asphaltic resinous composition and steady character. If no new spill occurred, an increase of the oil contamination level in observed years. These years indicated oil's ability to migrate in permafrost soil for a long time. Thank you.
Thank you, Yulia, for your presentation. Are there any questions? I would like to clarify one moment. You have a photo in your presentation where consequences of River Lena flood was illustrated. Are there full tanks with oil, or what was empty tanks during flood?
Я извиняюсь, я не поняла вопроса. Уже время.
The photo with fall down tank fall down. Yes, this photo is empty or full tanks with oil during the flood.
This case was in 2021 because was flooding at the Lena. This tank farm where storage oil and oil products.
Was there oil inside these tanks during the flood, or it was empty, abandoned tank, probably? Пустые это были
Нет, я поняла.
или полные? Вы не знаете?
Емкости были полные, да, и когда был, их просто сорвало с фундамента и унесло в реку.
Полной нефти, да?
Ну, где-то полный, где-то не полный. Был
но не пустые, да.
Да.
То есть это действующая...
Действующая нефтебаза, одна из самых крупных нефтебаз на реке Лена.
Okay, thank you very much. Are there any questions? No. Okay, so let's move to next presentation, and it will be given by Evgeny Olkhovik. Are you ready?
Да, коллеги, добрый день. Я сразу только вынужден извиниться. Я по-английски, к сожалению, не очень готов выступить, поэтому на русском языке выступлю. Значит, у нас, я представляю Государственный университет морского и речного флота имени адмирала Макарова, Санкт-Петербург. У нас традиционно все работы, посвященные Арктике, выполняются на одном из старейших арктических факультетов, который был в 30-е годы организован и до сих пор входит в состав университета. Ну, также, конечно, я за своих нескольких коллег, у нас несколько докладов не должно было быть, но не все из них состоялись. Я поэтому немножко пошире свой доклад, так сказать, сделал, потому что статьи выйдут, вы сможете прочитать. Вот. Но у нас основных как бы два направления, такие традиционные, классические. Первое, это, считается основное, это навигационно-гидрографическое обеспечение плавания по Северному морскому пути. И второе, которое мы сейчас активно развиваем, это исследование морской арктической транспортной системы. Так, сейчас видно слайды, да?
Yes, we can see your presentation.
Ну, Северный морской путь развивается. Естественно, там те задачи по существенному увеличению грузооборота, все понятно, все знают. Значит, мы внимательно все-таки следим по тому, не только за цифрами грузооборота, а то, каким образом растет количество судозаходов во все арктические порты. Значит, вот снизу как раз представлена диаграмма по, значит, одна это количество заявок, поданных в администрацию Северного морского пути, и по количеству реальных судов, которые в акватории Северного морского пути, значит, работали в течение года. Ну и видно, что постепенный такой рост идет, хотя как бы структура флота существенно меняется, много новых судов. И за последние 3 года количество судов с высоким ледовым классом, которые могут осуществлять постоянное круглогодичное судоходство, оно увеличилось. Их общая валовая вместимость уже превысила 3,5 миллиона тонн. Ну, тем не менее, есть там такие другие тенденции, что все-таки старые суда постепенно убывают, которые либо с низким ледовым классом, и которые требуют ледокольного сопровождения. Значит, основные инструменты, которые мы используем, понятно, что это технология GIS, геоинформационное моделирование. У нас достаточно большой архив как картографической информации, которую мы собирали, информации о движении судов и космических снимков. И все это мы постепенно, так сказать, обрабатываем, получаем какие-то архивные данные и, соответственно, разбиваем как по арктическим морям, как по различным судам различного класса, строим их треки, анализируем, накладываем, считаем, в каких морях какая интенсивность судоходства, в какие арктические порты заходят суда, ну и так далее. Ну и вот каким образом изменялись те грузовые потоки за последние несколько лет. Вот внизу видно, как существенно нарастило количество судоходов в порт Сабет. Здесь имеется в виду порт Сабет и новый порт. Это фактически один порт считается. И по 2020 году эта цифра уже превысила где-то там почти 1000 заходов. С введением уже терминала утренний это может достигать 1600 заходов. Но тем не менее другие порты, та же Дудинка или порты Восточного сектора, Певек, Тикси, они, конечно, прибавили, но не так значительно. Сверху вот показано количество судов, которые работали в течение года в акватории Северного морского пути. Понятно, что пик достигается в те 3-4 4 летних месяца, когда чистая вода в разы может превышать зимние, но тем не менее вот тенденция, она в принципе идет к тому, что постепенно период навигации летний, осенний, он постепенно расширяется. Но вот здесь более подробная информация. Снизу представлено количество судов между западным сектором и восточным сектором. В качестве такой границы, естественно, используется пролив Вилькицкого. Но мы видим, что восточный сектор у нас, к сожалению, он существенно отстает в своем развитии. А основное судоходство – это юго-западная часть Карского моря и Енисейский залив. Также мы, естественно, поскольку работаем с транспортными логистическими компаниями, внимательно занимаемся анализом скоростных режимов движения судов с различного класса. В основном используем данные, которые нам предоставляет либо администрация морского пути, либо, значит, спутниковая АИС. Значит, большинство транзитных рейсов мы неким образом, значит, зафиксируем, фиксируем в каких морях, в какой период, значит, каким образом изменяется скорость прохода судов, либо при самостоятельном плавании, либо при проводке ледоколов, ну и что позволяет, в общем-то, как идея на будущее, более точно прогнозировать, с какой скоростью, значит, могут сюда проходить те или иные маршруты. Значит, это пример вот скоростных режимов в Карском море, переход через Карские ворота в порт Сабетта. Значит, но если мы рассмотрим какие-то единичные проходы, как правило, сюда двигаются по так называемым рекомендованным маршрутам, это те тонкие линии на картах. Значит, по факту, естественно, сеть маршрутов, она гораздо сложнее, в зависимости от ледовой обстановки суда. Значит, если вот это маршрут классический, традиционный, летний, в период зимне-весенней навигации постепенно суда, значит, отклоняются от рекомендованных маршрутов, идут ближе либо к восточному, либо к западному берегу Ямала. Ну и когда уже обстановка непосредственно в Карском море становится достаточно сложной для судоходства, ну, начинается, значит, проход через Баренцево море, северные мысы Желания. Ну, это вот реальные треки за 2018 год, 1 месяц зимней навигации. Ну, естественно, дополнительно мы изучаем, насколько удлиняется сам маршрут, насколько происходит боковое отклонение от рекомендованной трассы, ну и так далее, другие параметры. Ну, естественно, у нас есть возможность получать космические снимки от спутников АМС-HD, АПСР-2. Мы, естественно, можем их совмещать, смотреть в зависимости от сплоченности льда, каким образом изменяются скоростные режимы, строить, выявлять те объемы, скажем так, операционной акватории, где в какой-то месяц суда, значит, проходили и работу, делать анализ такой по годам. Ну и, ну, скажем так, для эксплуатирующих компаний, естественно, это только красивые картинки, всем важен прогноз. И вот аккумуляция таких данных за несколько последних лет, она уже позволяет выявлять там тенденции. Вот здесь представлен там переход через, каким образом изменяется скорость. То есть мы видим, в Баренцевом море она близко максимально техническая для судна. Дальше Карские ворота, вот здесь уже вход в лед, дальше более тонкий лед и переход уже в узкую глубину. Ну, еще достаточно важный момент, поскольку у нас кромка льда сильно перемещается, мы при анализе сплоченности льда стараемся строить некие изолинии, они достаточно хорошо просматриваются на спутниковых снимках, и определять границы льда, и каким образом граница льда перемещается, естественно, тоже это влияет на скорость прохождения трассы и на время пребывания судов в пути. Ну, вот один из примеров. Здесь вот синими линиями те рекомендованные маршруты, которые используются в летнее время. Здесь вот зеленым видно это граница кромка льда, и значит, мы накладывали фактически маршруты, измеряли их скорость как по чистой воде, как и во льду с различной сплощенностью. Ну и большой объем данных позволяет нам анализировать их, естественно, за несколько лет и для каждого месяца. Ну, здесь на примере судов Норильского никеля вот видно, что месяца летней-осенней навигации июль, август, сентябрь, октябрь, разброс по скорости и по времени перехода достаточно небольшой. Значит, межнавигационный период ноябрь, декабрь, январь, естественно, падает и скорость, и падает то отклонение, которое, значит, мы видим по времени. Ну а самые, так сказать, тяжелые моменты для навигации, естественно, разброс, то есть вот переход Дудинка, Архангельск, он может там отличаться на двое суток. Это связано прежде всего и с, естественно, с снижением скорости, первое, второе, с изменением маршрута. Ну и, как правило, чем, так сказать, наша работа заканчивается, это некий прогноз по тем скоростным режимам, которые могут быть в различные месяца года. Естественно, пока данных, честно говоря, мало, но мы надеемся, что там в ближайшие 2-3 года мы из существующего опыта постараемся их добрать и уже сможем, значит, на каждый месяц, на каждую характерную какую-то ледовую обстановку давать, значит, более точный прогноз. Так, ну немножко могу показать, как происходит судоходство. Значит, ну вот это, естественно, зимняя весенняя навигация. Вот видно, это реальные треки судов. Значит, в начале зимы используется рекомендованный маршрут, потом, вот мы сейчас увидим сюда, начнут постепенно вот эта полоса, она расширяется, в какой-то момент практически прекратится, да, и вот, значит, при сложной ледовой обстановке, значит, используется уже проход через северную часть Баренцевого моря, через мыс Желание уже в Обскую губу или Енисейский залив. Здесь такой же процесс постепенно, то есть происходит расширение операционной акватории, боковое отклонение, то есть увеличивается и время перехода, и его, значит, протяженность. Так, ну, соответственно, для лета совершенно другая картина. Вся акватория Северного морского пути используется. Значит, те треки, которые идут севернее Новосибирских островов, это, как правило, сюда с большой осадкой. Но основная, как бы, интенсивность, она за счет судов класса река-море, которые, кстати говоря, не покидают, как правило, акваторию и моря Лаптевых, Восточно-Сибирского, и Чукотского моря, она сосредоточена, вот, видите, красным цветом, такие вот более интенсивные. Это, значит, для восточного сектора береговые трассы, но работа, как бы, в западной части, она постоянно одна и та же, то есть это те маршруты, которые будут в Обскую губу или Тузу. Доклад закончил, готов какие-то вопросы ответить. Сразу еще раз извиняюсь, что сожалению, не удалось выступить хорошо на английском языке. Спасибо.
Thank you, Evgeny, for your presentation. Are there any questions? Сергей Викторович? Yes, please.
Ну, если можно, я тогда тоже по-русски, ну, попробую перевести. А скажите, удается вам увидеть, вот вы так следите внимательно, какие-то высокоширотные проходы? Я понимаю, что это вряд ли наши суда. Вот я помню, внимательно следил за китайским стареньким ледоколом. Однажды он, так сказать, проходил там сверху. Как часто это вообще бывает? Вы же всю как бы картину видите.
Вы имеете в виду в какой период? Зимой?
Нет. Ну, в летнее время высокоширотные вообще вне экономической зоны туда поднимаются наверх и идут. Это часто бывает? Я просто только один раз видел.
Слушайте, последние годы, да, чаще. Но на самом деле, если смотреть вот период такой за последние 10 лет,
да,
то есть совершенно четко было, скажем так, несколько лет вообще не было проходов, ну, я имею в виду по высокоширотным трассам. Последние годы, да, с появлением судов там Ямал-СПГ, они там чаще.
То есть...
Но все равно это, скажем так, это разовый, то есть это там в течение лета 15-20 проходов, не более того. Плюс какой-то, по-моему, 18-й год был, скажем так, окно безлюдное, севернее Новосибирских островов, оно длилось буквально 30-40 дней. То есть обычно это, там, например, 90 дней мы четко определяем. Если пролив Садникова там почти 100 дней, то по высокоширотным трассам там еще меньше. Ну и здесь как бы вторая задача, про которую не рассказал, все-таки НГО, то, что навигационно-гидрографическое обеспечение занимаемся. Там, конечно, не все обследовано, мы не знаем, какие там глубины, какая обстановка, нету там точных прогнозов по ледовой обстановке, ну и так далее. Не всегда есть даже спутниковые снимки, они там, если в каком-то свободном доступе каждый день их точно нет, то есть это может быть через день, через два. Ну, пока информационного обеспечения недостаточно. Если бы оно было лучше, я думаю, что и проходов было бы больше количества.
Спасибо.
Thank you very much. Are there any questions? I guess that's all. Thank you very much, Evgeny.
Спасибо.
Anastasia Magaeva still has problems with internet connection, so probably she should contact with Alexey Maslakov, and she will give her presentation tomorrow. So our session is finished. Thank you very much, all participants of session.
Коллеги, большое спасибо. Всего хорошего.
Goodbye.